guys. Welcome to SkyTour live stream. How are you, everybody? It is a beautiful February 26th. February's almost gone. You know what that means? It means that we're getting that much closer to galaxy season. But we still have plenty of things to see tonight. I want to welcome our cohort in Astro Crime, Daryl Mason. Hello, Daryl. How are you?
Hello, Mark. I'm good. You? Hello, everybody.
I'm doing fine, thanks. It's good to see everybody out here tonight. And we'll have some fun tonight. Yeah, this guy right here is a really neat object. Okay, this object is really interesting. Okay, it's a planetary nebula. It's a nebula that's actually the remains of a dying star. All right, actually a star that has since died, and it is called Jones Emberson 1. And what it is it's a planetary nebula, and they are named so because they look like, in a small telescope, if you could see them in a small telescope, they resemble faint planets. So that's how that came to be. It's really a bad name for it. It should be, maybe they should have called it a SR nebula, a stellar remnant nebula, or something like that. But they didn't, so it's okay.
I think they should call it the Headphone Nebula.
Well, actually, that's actually a name it has, right? It's sometimes called the Headphone Nebula.
Yeah, I know.
Yeah, so it's cool. It's really neat.
That is really neat.
Yeah.
And up another one. First time for me, first time for you.
That's right. I've never seen this particular one before. This is from the PK catalog, okay, online that you can look at the PK catalog. It's a beautiful object, and let me just actually throw this out here for you. Let me just slide that right out there. There we go. This is Jones Emberson 1. It's a planetary nebula. It's, I believe, several thousand light years away. And we have to...
1,500, 1,500.
Okay, yeah. So it's about the same distance, I think, as the Dumbbell Nebula.
I forget the dumbbell.
I think it's about 1,500 as well, but you can look that up. Now, if you notice, they have these weird symmetric shapes, right? They have this strange symmetric shape. It looks like it comes in at a waistline here, kind of reminiscent of the Dumbbell Nebula, right? Which has the same kind of hourglass look. I'm going to guess that this nebula is classified as one that's called bipolar. And it doesn't have anything to do with its personality, of course, but it has to do with the fact that it looks like it has a symmetric lobes across the center at some point. And that's just what it looks like here. So Jones Emberson 1 does seem to fit that particular finding, that particular topology. And let me just give us a little more data to look at here.
I think that's a very nice planetary nebula.
It is. I have 16 stacked images here in over 35 seconds. So I have been taking pictures of this before you guys came on board with us. So that's that. I did want to say hello to Michael Hedrick, who was the first one here. You are a superstar, man. Good to see you. And DPFX 9999 is here as well. Nice to see you, brother. And of course, Michael has a few comments he made. I'll come back to those, I hope. Pedijur 17, hello, how are you? Welcome to SkyTour Livestream. Make sure you subscribe. See, click the thumbs up, give us a subscribe there, and hang out with us. We show you astronomy. Actually, you know what? We have a new tagline for what we do. The universe in real time. And I think that's really what we are. We're creating and showing you the universe in real time. This is not. This is real time. This is now. Okay, the light we're seeing traveled 1,500 years to get here, intercepted our telescope, and we're capturing it. For all we know, we're the only ones in the world right now looking at this object at this moment. And we're seeing it live, and that's kind of cool. But there's a lot of people on the planet, but only on the night side can they be doing this right now. So there might be others.
Lugo asked what the focal length is.
The focal length in our telescope right now is 503 millimeters. Now that's a Richfield telescope because we made it Richfield. It used to be an f8. Okay, so the focal length was a lot higher, and we literally cut it way down to allow us to see massive fields. This is a close-up. We're at 118% on our sensor right now. Let me show you what it looks like if we were to just, show you the whole sensor. This is the entire sensor right here. This is 4 full moons across and 3 full moons tall. Okay? 4 full moons across and 3 full moons tall. So we're not designed to look at little tiny things like planets. We're designed to look at large, extensive things like vast nebulae, vast dark clouds in the universe. And our telescope is well suited to find those because it is looking at such a vast size that we can actually capture more light, about 25 times more, in the same amount of time that it would take the original configuration to capture light. So our telescope is 25 times faster than it was before. And believe it or not, right now, and this may change over time, but this particular telescope that you see over my head right now is the only one on Earth that's actually modified for the Meade, M-E-A-D-E, the Meade line of telescopes, to have this particular F2 enhancement on it, the system, the hyperstar system. There's no other Meade telescope that has it except ours. And we were the actual, the prototype for this whole process. So, hello Cyclone, hello there, I see you there now, and I also, this guy Daryl keeps in the chat. Who's Daryl? It's you, obviously. And I saw that we had Sam S is with us. Hiya, Sam. Renee Cruz is with us. Hello, Renee. How are you doing? I believe you're down there in Brazil. All right. Donald Kunzer's with us. Daisy and Zoe Amethyst. Hello, guys. And it's so good to see you. And Lubo in China, thank you for that question before. That was a really, really good question. And he writes, Lubo writes, could you write in the video description of the parameters of the telescope? I will, actually. That's a very good point. I should do that, and I will. Thank you for that comment. That's a really useful comment, and I should do that. And, okay. And Daryl said 10-inch f8, Schmidt Cassegrain working at f2. That is pretty much, I would write that as well. And he says, yeah, it's a great object for an f10 telescope, although it'll take a lot longer to gather what we see here. We're doing a 35-second exposure, and we're capturing almost all the detail this has to offer. So that's pretty good. That's pretty good. There, now that we got more, we can actually do a color correction to get the proper colors. And as we zoom in now, it'll support zooming in a little better. See that blue dot right there? That blue dot is really impressive. That little tiny guy, all right? And we're talking about this little guy right here, all right? That blue star right there is what's known as a white dwarf. It's the remains of a star just slightly larger than the sun, or well, just over 3/4 the size of the sun, after it sloughs off its outer layers as it reaches old age, and then the core contracts, leaving behind the outer layers, which continue to move off the star. And it's a very, very hot core. And it's not a real, they call it a white dwarf star, but the stars are doing nuclear fusion. The white dwarf is not. It's actually held up by a special process called electron degeneracy. And in more massive stars, that's neutrons that do all that holding up and forcing outward to keep the star held up. But electron degeneracy is like having a checkerboard where all the squares are filled with an electron, and you can't compress them anymore. You can't have 2 electrons in a checker square. Only 1 checker per square. So you can imagine if you compress those all together, that's as far as they can go. So the star is trying to collapse because it has so much gravity and so much mass, right? But that collapse is halted by the electrons pushing outward from their checkerboard squares, and they can't be crushed any further because the star isn't mass enough to go any further. And that magic number is 1.44 times the solar mass. That is the mass of the sun. If the core got heavier than 1.44 solar masses, it could continue to collapse or do other things. And so what we see right here is just a white dwarf that results from that collapse to what we call that electron degeneracy stage, which is what we're seeing here. And again, the shape is dictated by things like the rotation of the star originally. I'm going to guess the star was rotating along this axis, and if I had to make a guess, I would say it's probably this is the axis of the star right here. And I don't mean the North Pole and South Pole. I mean, I should actually have drawn that, huh? I probably should have done that. That's a better thing to do. So let me show you the North Pole and South Pole axis. I think it's right here. I think that's the North Pole.
Was like it's the sun's equatorial axis to start.
Yeah. I think this... yeah, I could have said it, but I wanted to make sure that if people think about a globe that has the axle for like a globe, an Earth globe.
Yeah.
I think one of these is north and one of these is south, and this is the equatorial region. It's gone whipping out, and these are the areas that have a buildup of material, but it's not as forcefully thrown out as the equatorial region is. So it's spinning in some way like this, okay? Not the whole nebula, but the star. So it was sloughing off this material in that direction in that way. There's so much to this.
Axis of rotation.
Axis of rotation of the star, correct. Yeah, exactly right. No, so that's pretty much what we talk about. You know, we're talking about all these things. I want to say hi to Bullwinkle, who's here with us as well. And Terry is here. Hey, Terry Haig, how are you? And Terry Haig is a cat person. That's why she has a little kitty cat next to her name. I know Terry. She's a recent convert to SkyTour LiveStream.
Cool.
Yep.
Question.
Yeah.
Have you run your focuser yet?
I have not yet. I'm going to do that, but I had checked the focus, and I noticed that it was fairly close, and I just was doing this to try and get as close as we could get, and it looks pretty good.
Might do your temperature compensation too.
Yeah, I don't have that on yet. We're at 9.75 degrees out there Celsius, as you can see right here. And that's a good thing to mention too, you know, for those that are new to our stream and for those that want a reminder. Okay, this is our telescope control block up here. Okay, all of the telescope controls are up here, and you'll see me referring to them often. This right here, this black box right now, that's actually a camera that is tuned only to the telescope computer. This is the telescope in the building right there. This is me 2,500 miles away from that telescope. I'm in Connecticut. The telescope is in the Arizona desert. This is our data collection. This is our stacking process going on. We can adjust parameters. We can play with these curves to try and get more data out, coax it out. This, of course, is the main view. This is the camera control section right here. All right, right there. And this is our focus control section. And then down here are other parameters. So that is a grand tour of what we have going on here. All right. So that all said, I'm very impressed with Jones Emerson 1. It's beautiful.
It is.
Yeah, I'm going to pause this now, and I'm going to make a note, because one of the things you're going to notice when I tell you here is that we will be providing you with some of these images. All right. Our costs are going up too. Starlink, which we use out there, has gone up, unfortunately, and we're going to have to recoup that cost somehow. So we have to figure out a way to do that. But let me just say this now. All right, when I hit save, it's going up to our server, and then I'll save exactly as seen. And there we go. Now that means that the image you see right here on the screen, exactly this, will go up to the server, and you can get this image and have it and hang out with it and enjoy it, put it on your desktop, whatever. However, if you were meant to see this or wanted to see this in a far better way, we do have all highly processed images. You can get them by going to skytourlive.org, and in the upper left-hand corner, you'll go to SkyTour LiveStream, which is here, or from skytourlive.org to the upper right, you'll see a Patreon page. We really need some Patreon subscribers to help us out monthly. And I think that would be very, very good for us, because then we can start to provide you with some really good images and not have to make you pay for the images you might want to see. If you just want to hang out and watch, that's always free. Anyway, we'll keep you posted on that as we move forward. In any case, what I'm going to do now is I will do a focus run. But if you notice, we have Jones Emerson 1 here, and we have this guy over here, you notice. We have a little
galaxy.
Yeah, that's right. We have a little galaxy over here. And if you want to know what that galaxy is, we go to our other screen that is part of our stuff that we do, and that is this screen here. This is our planetarium. Well, it was our planetarium program. Let me bring it back. It's our planetarium program here that connects to our telescope, and that galaxy we're seeing is right here. You see the writing here? Okay. If the writing is upside down, you have to kind of crane your head around to see where we're looking. That may not be the galaxy we're looking at. It might be a fainter galaxy out there. So we'll be able to see it in just a sec. Waiting for our internet. We're getting intermittent internet sometimes. That's all. That's okay. Okay.
Galaxy down at the bottom lower right, would that correspond?
Well, there's one right here too. You can't see it. First of all, let me just pull away the ID here for a minute. Come out there, thank you. And right there, you see another one, another pair of them. Okay. All right. So if we come back here, all right, let's zoom out a little bit. There's our. Let's go to the full screen so you can see what I'm talking about. Okay. All right. So from here, we have this galaxy down here, and that's directly below this. And there should have been another one up here somewhere. Yeah, I know. I'm not stacking right now. Okay. We know this galaxy right here. We know this galaxy right here. Now, if it doesn't show up on our planetarium program, it's because we don't have the proper star catalogs loaded, perhaps. But that's okay. Okay, the way this goes, all right, if you see the writing here, that's the field of view. This square box, this red box, is the field of view of our telescope. All right, so if we move this over and we center it right there, okay, that right there is where we're looking. And then if we zoom in a little bit, all right, we should be able to see that on the left edge of the field there should be a galaxy, but it's not there because our telescope might be a little off center. But I can move this around to see if it's there, and it doesn't much matter because we can usually find these things pretty easily. But that's just beautiful. That's really pretty. I'm liking it. But here's what I'm going to do. I'm going to clear this and go get rid of our stack. And for those who want to know what the stack is, it's very simple. When we take a photograph, that is something that will, say, go for 10, 20, 30 seconds, 40 seconds, even minutes sometimes. And after that photo is taken, it's there. And then we take a second one. We align it to the first and stack it on top. And we make an image sandwich of many images on top of each other. By doing that, we get rid of the noise. If you look at this image, the stars stay constant, but you see like a little flicker, and you see a satellite or two. Okay, that little flicker is the noise that's on the sensor. And by adding these images together, that noise gets canceled out, and you end up seeing a beautiful, smooth image. And that's what we do. That's what stacking does for us. It allows us to see fainter details that you might otherwise miss. Pretty cool. Okay.
Interesting. I see the diagonal streaks.
Yeah, they're not there really, actually. Okay. In the images. So, we're going to pull this out now. And you'll see that we get donuts now. We've gone out of focus now. So what we're going to do is we're going to take that and go in. And we're going to scan. All right. And we're going to let it autofocus. All right. And now this is going to get us a critical focus. So it's going to build a parabola, a curve like this. Okay. And that curve, at the bottommost part of that curve, that's the most sharp focus we can have. And as we do that, let me, okay, we've got enough stars. Okay, as we do that, it'll automatically find the best interpolated spot, wherever that might be on that curve, and it'll move the focus to that. And we will now have, at that point, perfect focus. Hello, Maya Leone, how are you? Marcin Johansson, how are you? Tim F, hey, good to see you, man. Did I see the Cosmic Ray's here as well?
He is or was.
Hey, Cosmic Ray, how are you? Nice to see you. Okay, now we have over 130 stars that we're using as a focus arrangement. We're seeing the curve it's building here. Okay, so it's getting more and more and more in focus, and it goes into focus, and it starts to go out of focus. You'll see that curve going up, and then that curve will get averaged. You'll see the curve very clearly, and then we'll have a line in the middle where the absolute perfect focus is. There it is. That is our focal point. And we're going to wait for this to be finished, and then we can tell it to go to the best focus position. And we're done. And so now we go to best focus, and now the telescope's going to go rack backwards all the way to the outermost part, and then back to the innermost segment where it's the sharpest focus, and there we are. So now we have perfectly sharp focus, and we're doing that from 2,500 miles away. It's a critical thing that you need to be able to do. Critical thing. All right, let's see now. Ray says these could be galaxies PGC 22186 and PGC 139. Yeah, it could be. You're right, Ray. I didn't take the time to look at the catalogs to see what those were. The ones down the bottom are definitely more than one. There's two down there at least, you know. Anyway, let's now do a 55-second shot of this nebula right now. The nebula's right there. I know it's faint, but you can see it. All right. So here we go. We're off and running. Now, how do you know we're actually taking the image, right? That's the question. You want to know how we're taking the image, or how you know we're taking the image. Because down here at the lower right, okay, let me just show you here. Okay, over here, this is our counter. You can see our counter right there, the progress bar. All right. So everything up here is good. Everything up here is good. And I'll just hide over here in the corner. So just ignore me. No, don't ignore me. I don't know. All right. Next thing we'll do is take care of making sure that our images are coming in nice and clean. The wind out there is not that bad tonight. Usually we'll see wind show up at some point. But right now it's not out there. Not out there at all. But, you know, it could be. You know, could be coming in soon. All right, let me move myself out of my way here. Remember, go to SkyTourLive.org. We really need Patreon subscribers to continue doing SkyTour. We really, really would like to welcome you into the SkyTour family. And you get stuff for that. You get very highly processed images for free. Well, it's not for free. You're subscribing to the Patreon, right? And those images start at $10 a month. And you get shout-outs for anything less, which I think is fine. You know, we have a few patrons so far. Okay, these are some of our patrons now. We have John P, Izabela M, Ali B, Chief Max Cyber, Vera Campos, Ronald, Martin W, and Raymond B. And, you know, it's a small list. But, you know what? We're growing. We grow on people, don't we? So here comes, we're 5 seconds from our first image here. 55 seconds. And I'll show you a couple other parameters that are very important. Okay, there we go. All right, that's really good. And now what I'll do is do a little processing here. Okay, so that's the first image. You'll notice the image is good. This is our data curve down here. This part right here, this line right here, this is the line intercepting the data. This line adjusts our black level. Right? If this line goes way out here, then we allow the background to be brighter. Right? Sometimes we need that. If we want to darken it up and get contrast, well, then we bring it closer to the peak. Okay, the average peak is this line right here. So this is the average data right here. Right? And then this guy is our mid-level. If we bring this in, you'll notice that we get a lot more detail at deeper levels in the image, and you can easily overwhelm things with that. So we leave that out for a while until we have more data, and so when we can zoom in without penalty. Okay, so we now have 2, and now that we have 2 stacked, you'll notice that the data has suddenly become even better. And now we can already see the white dwarf in the center here. Okay, but we still see noise. That'll disappear over time. All right, now I did want to take a moment to show you one more thing while we're here, and that is this. Okay, if you look at this entry right here, okay, this is the exposure. And the exposure is really important, okay? This is the one of the main things that we care about, right? And the other thing that we care about is the gain right here. Okay, the gain is set right now to 300, and the exposure is set to 55 seconds. So we play back and forth between the gain and the exposure here, all right? And those will give us the images that we look for here, all right?
Can't see the gain. Your little blue bar is in the way.
No one else sees that except you.
Okay, be that way.
Yeah. Yeah, Daryl is getting a screen share from me right now, so he has
Now
some
I see
things.
it.
He has some things blocking his view that you guys don't get to see. It's all stuff that no one cares about but me.
I care.
Well, you know what I mean. Yeah, cosmic ray, they are very dim, magnitude 17, magnitude 14, which gives you an idea of the performance of our system. It's really quite good. Not bad. So look at that, 4 stacked images. Look at the details in here. Not bad. I like that. Again, where are we? Well, we are at this strange nebula we've never seen before, Jones Emberson 1. Interesting. This is cool.
I hope Izabela gets to see this.
Well, she will either after the fact or during the show.
Yeah.
The other thing, too, I wanted to mention is that this also has a PK number as well. There's a PK value to this as well. There's a PK catalog. And this is PK 1. PK 137, is it? PK, oh yeah, PK 164, and then the plus 31.1, that's actually another part of its designation. And you also have a PN number, okay, and so it comes from, that's the planetary nebula, of course, but it gives you all that information. Okay. If anyone has any questions, feel free to toss them into the chat. Let's go back here. Let's see where we are in terms of center. Yeah, okay, so we're a little off center. That's okay. All right. And away we go. Move this down. See that image that just came in on the 6th one? Now it's starting to look better and better and better. Let's do a little bit of color correction here as well. Here we go.
Cyclone asks, what is the program that you use?
Oh, if you're talking about this, all these here, okay, this program here, the one that I'm operating the camera with, is what's called Sharp Cap. This one here is APT, astrophotography tool. This is a security camera system that I have in there, and that does all the things. Now, in the background, what you don't see are these little housekeeping things. This is part of a program that I wrote to actually run the physical observatory. You know, have the roof roll on and off, turn the telescope on and off, make some adjustments to the computer, etc., etc. I have all that together makes the observatory, and I needed all of that to make this all work right. Okay.
Can you zoom in a little more?
Yeah, I think we have 8 here, so I think we can zoom in to check this out a little more. Okay, that's too far a little bit, but because we're still getting some problems. What I could do though is I could try some enhancements. Let's add an unsharp mask enhancement to try and sharpen up those clouds. There you go. So now you can see areas. Now it adds a little mess there, but we can add a bilateral filter to cut down on that, and you can see that. Now I can zoom out a little bit actually, just to turn off the bilateral filter. Okay, let's do that. Yeah, see how sharp those are? And we come into the histogram now. This is our data, and let's get rid of the noise in the background by pulling our dark background in, and then taking this down just a little bit. There we go. And we can actually pull this back a little bit. Modify this a little. You can really see that blue neutron star. I'm sorry, a blue white dwarf in there. And blue, the blue color is due to its temperature. Stellar core is exceedingly hot, and this stellar core is so hot that it's in the blue end of the spectrum, and blue is the hottest color. Red is the coolest color, believe it or not. I know fire is sort of reddish orange. It's actually quite cool. It's not hot. Very hot is the base of a Bunsen burner flame, which is that nice dark, that nice shade of blue. That's the hottest part of the flame. Similarly, in stellar interiors, okay, the hottest part of the star will be blue, and there are stars that are in fact quite blue, and much of their radiation they give off is going to be well past the visible part of the spectrum in the blue ultraviolet range. You know, O stars, for instance, Alnitak, the leftmost star in Orion's belt. Oh man, that's like an 09, 07. That's a, you know, O is the hottest and M is the coolest, and it's OBAFGKM. And the sun is a G-type star. All right, and this star here is a white dwarf star, and it doesn't look very bright. All right, when you look at it in a telescope, you might not really see it. However, it's also only about the size of the Earth, and at 1,500 light years away, okay, that's 1,500, okay, times 6 trillion miles, okay. That's how far away it is in miles. And when you look at that, to be able to see a star the size of the Earth, that is the core of a star, the size of the Earth, from that much distance, it has to be extremely hot and luminous to see it. And it's small. It's only the size of the Earth, so it's really, really got a lot of energy it's giving off. And that energy is what causes this glow of the gas that used to be part of the star when it was a star. The red is hydrogen, the green is oxygen, and when you ionize atoms or nuclei, when you ionize atoms and they become nuclei, then the electron from a hydrogen atom leaves the hydrogen atom, goes out, bumps into other particles, comes back into the hydrogen atom. So it absorbs energy to go off. But then as it loses energy out there, it comes back in. And as it comes back into the atom, it cascades down several energy levels, several discrete quanta of energy levels, which is why we call it quantum mechanics. All right, we talk about atomic structure and atomic physics. It's quantum because there's defined separate energy levels. You can't have them in between. They only go to specific locations. So the electron cascades down, and when hydrogen does that, it goes to a level that makes an orange glow, because as it cascades down, it gives off light. And it gives off a specific light in the red end of the spectrum when an electron for hydrogen cascades in. Oxygen does the same. This is doubly ionized, and it gives off a green glow. Really pretty. Yeah, these. Yeah, go ahead.
Pardon me. Marston asked an interesting question. How long would it take to cool down to a black dwarf? It'll take a really long time.
We've never seen one.
I was going to say, yeah, I don't think they've actually seen one.
Yeah.
Of course, it's black, but the cool down time, you're probably talking comparable to the age of the universe, I dare say.
Yeah, and in fact, on the other end of the spectrum, if you look at stars like these little tiny red ones here, like that one maybe, or these two over here, or these guys, these red stars, these might be those stars at the other end of the hot spectrum, down at in the M range. M as in Mike, okay? And the M stars, they are so slow at using up their hydrogen fuel that, in fact, they have more access to their hydrogen fuel, as I'll explain. They're so slow at doing that not a single one of those stars that was born when the universe was born has even died yet, because they last trillions of years, not billions of years. The universe is 13.8 billion years old, and the oldest M star in existence that ever existed is still in existence. So, and they're the most plentiful star in the universe. So we've got a lot of stars out there that are M stars. In fact, most of the stars in the universe are these very tiny little percolators. And so we found more planets around those than we have around any other type of star. Stands to reason that they're the most plentiful, that's why. Terry says, beautiful. Yeah, it is, isn't it? And as Daryl said, they call this the Headphone Nebula. And you can see why.
We're right on the edge of fine detail in
yeah,
like
you can start to see it.
The bottom right, the upper left.
Yeah.
I see a little skinny divider.
Right here?
Yes, in the middle of the one on the lower right.
Yeah, I see that.
And fine details
there.
in the clouds to the left and right also.
Yeah. And the more the longer we go, the clearer that detail becomes.
Folks, you heard Mark talk earlier about electron degeneracy pressure. That's blue star you see in the middle, the white dwarf. That was roughly a sun-sized star, and what's left of it collapsed down to the white dwarf. As he said, it's about the size of the Earth. If you wanted to go the next step, if you made the star 1.4 plus solar masses,
yeah, 1.44, yeah.
You went from electron degeneracy pressure to neutron degeneracy pressure. And instead of being the size of the Earth, you have shrunk that star down to the size of Manhattan Island.
That's right.
And that's the magnitude jump right there. It's so much more extreme. And by the time you get down to the neutron star, well, that sucker's putting out X-rays and all sorts of good hot stuff.
It is. And on top of that, the neutron star tends to be a rapid rotator because they're made through the most violent means. They're made through the explosion of the star. And on our SkyTour radio, which you can get to again by going to skytourlive.org, our Sunday night show, which we didn't do tonight because of one reason or another, but the neutron stars tend to be rapid rotators because when the star explodes, there's a lot of pressures on the star, and it collapses very rapidly. The core of the star, the very center of the star, the core, like the blue thing you see right here, okay? Those collapse so rapidly. Imagine an ice skater pulling the arms in. What do? They spin faster and faster, right? It's called angular momentum. And that angular momentum, in order to be conserved, the spin has to increase, right? So when you see this spin increase, we see neutron stars that are spinning in the Crab Nebula case, the Crab pulsar there, which we'll explain in a sec. In the Crab Nebula, 33 times per second. There's another pulsar out there, another rapidly spinning neutron star with a lighthouse beacon of hotspot energy on it. That's what a pulsar is. And every time it passes, it flashes us, Psh, psh, psh. But imagine one doing that over 700 times per second. There are neutron stars out there spinning that fast. That's incredible. And what that means...
I'm sorry, go ahead.
What that means is that we would have a Manhattan Island-sized object spinning over 715 or more times per second. That's a lot of mass held together. Why doesn't it just fly apart? It doesn't fly apart because the neutron degeneracy pressure resists the compression further, but the compression is coming from the massive gravitational field. Massive gravity trying to compress it can support that rapid a spin. That's how much mass is in it. And a teaspoonful, if you could take it off the star, you could never do that in reality, but let's just say you could. And you brought it to the Earth, it would weigh several billion, with a B, tons. Go ahead, Daryl, I'm sorry.
And to continue that line of thought, if you were able to get that teaspoonful of neutronium off the neutron star, it would decompress instantaneously.
Oh, yeah.
Because all that gravity is no longer there to hold it together.
Right.
And you would see a great big bada boom.
Yeah.
Talking about neutron stars, there's been one in the press recently. Anton Petrov on YouTube did a episode on it just recently, and I've seen it elsewhere. Two neutron stars collided recently, and they formed one great big neutron star. And they were scratching their heads because it maintained a spherical shape. When the two neutron stars, bonded together and made one great big one. And there has been talk of this, that the only thing keeping this neutron star from collapsing to a black hole is its spin rate. It is spinning so fast that it has yet to cross the event horizon, I guess, and it is inevitably going to slow down and turn into a black hole. But right now it's still just barely maintaining. It's on the very, very edge of leaving us forever.
That's very cool.
Going to black hole land.
Cosmic Ray says that's 42,000 RPM, revolutions per minute. Do you know of anything here on Earth that spins that fast? Some industrial machines, mostly there's some crystal structures that are used to do that. Hello, C&D Boy. Hello, Simon Thompson. Hello, David Schmidt. Hello, Mark Nelson. Good to see you guys. Thanks for joining us. David Galish, how are you? Nice to see you as well. Yeah, so we have a tremendous amount of stuff that we like to show you guys and teach you. I just went, to this screen just to kind of show you the details here because we're starting to see them now and it looks really good. Let's get back to the telescope here because we're going to be moving on here shortly. We have 22 of these stacked, so I'm going to stop and get it back, get it saved out here. Okay, so let's save it.
Looks too cool looking.
Isn't that nice? A lot of detail.
I have a suggestion for when you leave here.
Yeah? Another object?
Yes.
Okay. Well, we're in the constellation Lynx, which is out in the northeastern part of the sky, Okay, that wall you see right here in the observatory, this is the northern wall. This is the eastern wall. The southern wall we're looking from, and the western wall is over here on the left side. You can't see it, it's way outside the view. Okay, because we have that much detail in there. So we're save the astronomical file format, and then we're going to save exactly as seen right there. Nice, nice, nice. Mark Nelson says, saw a beautiful view of Jupiter and Venus almost in conjunction tonight. Hope to photograph them tomorrow. Yeah, Venus and Jupiter were interesting in the sky. They look really pretty. It was even prettier a couple days ago when the moon was also joining them in the sky. That was actually really pretty too.
Yeah, I meant to mention that.
Yeah.
Folks, yeah, I went out and looked at it tonight for the show, and they're 2 fingers apart right now, and they're going to get even closer on Wednesday evening after sunset, March the 1st. Venus and Jupiter will be at their closest. They'll be in conjunction, at which time they'll be a half a degree apart. That's about a lunar diameter, and that you can cover that with your fingertip at arm's length.
That's right.
And that should make for a really pretty picture.
Nice.
I'm not sure the weather's going to cooperate here, but I've been watching this coming on for a while.
Okay, let's go to our planetarium now. And you have an object you'd like to look at?
I do. I'm going to post a link as soon as it comes up for the server. Maya Leone is here, and she reminded me. You want to go take a look at the Medusa Nebula again?
Oh, sure, Medusa Nebula. That's a really pretty object. I was looking at that earlier in the just in our program here to see where it was relative to where we are, and it's actually finely placed.
Yeah.
It's well placed.
Still the same general area of sky, isn't it?
Yeah.
Okay.
Little better placement, though. Okay, there's the Medusa Nebula. I'll back out so you can see where we're going to be looking. We're going to be looking, see, we're out here, we're up in the northeast. We're going to be looking now more to just southeast slightly. Okay, so when you watch, you're going to see the telescope swing right around here if you're ready. So we'll see that happen in just a sec. Okay, well, we're going to...
You saved the image, didn't you?
I did.
I don't see it showing up at the...
Well, it's because our session... Yeah, we have to wait a sec here.
All right. Patience.
Patience indeed. There we go.
I will post it when it shows up.
It will. Okay, let's go here now and watch the telescope swing around. Okay, here it comes. Off we go. And the Medusa Nebula is another fine example of a beautiful nebula that is really exciting to look at. And you will see it here. There it is. All right, we're going to move that into the center just a little bit. There we go. All right, we move a little south. Now we're going to move a little east. You can see that little fuzzy right there. That's our guy.
I see it.
Yep. All right. Now, once we're here, you'll see it says searching right up there. It's searching. It's going to find a guide star, lock on, and away it goes. There we go. We're guiding. Once it's stable, I will proceed to get it. I'll proceed to get it going. Until then, I'm just going to do one more thing. There we go. I just reinitialized a few things. Okay, good. All right, well, there is our nebula. We're guiding well, and I'm going to make this a 45-second shot. All right, and it's off and running. You'll see down there our yellow bar is moving across, and we're going to see this guy right here. All right, and we can compare its size to the size of the previous one that we just saw. So let's live stack this. All right, this is our previous one that we just saw. This is the buffer with the previous one in it. And we'll clear this out, and you'll see the next one coming up. And I'll clear this as soon as we get near. We have 10 seconds to go. Now, when I get to 5 seconds, I'll clear this so we can remember what it looks like. There we go. So I'll clear it now. Now watch the next one come in. There we go. All right, so here it is. This is now a different nebula called the Medusa Nebula. Really fascinating place, really interesting nebula. Let me just get us down here. There we go. Okay. And we'll pull this in. The Medusa Nebula is really pretty, and we'll see that here shortly. And again, we're at 300 gain, 45 seconds. Look at that. That's really pretty. The Medusa Nebula is another one of these planetary nebulae. And it's just got a lot of interesting detail, just like the Jones-Emerson one does. And I'll just do some housekeeping here for you guys. All right, and throw that out there right now. There you go. Medusa Nebula. Josh Rutledge is with us. Torque, how you doing, man? Josh has a great show, a great podcast called The Convergence Zone, right? And I've been on the show a couple times now. It's really a great show. They do their homework. So if you, Josh, you're a media moderator, so please put up your link so people can go find you. Medusa Nebula distance from us, Mark Nelson asked. It's going to be a couple thousand. Yeah, go ahead.
Also, 1,500 light years away.
Yeah, okay, so it's about the same. Yeah, and let's see here. This is
Google is your friend.
Yeah, Google is your friend. Yeah, okay. And we'll zoom in on this now. You'll notice that this particular nebula has a lot of really incredible detail. Look at that detail.
I'd still say it looks like a chili pepper.
It does look like a chili pepper. Oh, Casa Gray says, you ready to shovel snow tomorrow night? No, Ray, I'm not. You know, I sold my tractor, too. I have a tractor with a bucket and a backhoe, and I used to just go down there with a bucket and be done. Well, I sold it, and now I have to actually rely on four-wheel drives to get down the driveway.
Uh-oh.
That's okay. Yeah, Josh, put up your link, please. Look at that. This is only five exposures in, and we got a lot of detail already. Look at that.
Yeah. Now, which star did we think is the central star?
Oh, we know which one it is. I'll show you. It's this blue one right here, once again.
Yep. I was going to say the blue one.
Yep. See, look at that. So right there, that's another beautiful white dwarf star. And this is another planetary nebula, just like the one we just saw. So we've had two planetary nebulae that we've looked at here. And they're both extremely hot. There it is. He put it up there. It's the Convergence Enigma. You know, I knew it was. I knew that it was Enigma. My apology. Convergence Enigma is Josh Rutledge's show. Go check that out if you can. Put a link in. Go check it out.
That is really cool looking.
That's really pretty, yeah. Yeah, no C&D boy. No more Clem. Oh, that tractor. It's funny you found that. That tractor, that lawn tractor, is dead and gone, because of course it went over the edge with Clem on it. But we do have another one. That's beautiful. You can really see this beautiful blue white dwarf, which is right here. See that blue star inside that square? Right there. That's the white dwarf. Again, for a star, a remnant of a star that's 1,500 plus light years away, that's bright to be seen from that distance, in that it's only the size of the Earth. I always found it fascinating when we look at these things. You look at the light coming from them, and the bottom line is you're looking at this light, and as you watch the light, you're saying, I say to myself anyway, because I'm weird that way, I'll say things like, this particular object, okay, we're seeing the light coming from it, and I'll just soften it just a bit to get rid of the noise. Here we go, right about there. Okay, we're seeing the light from this. This light comes to our telescope, right? And then when we go to the next object, it's still streaming light to us. But there's no one there to see it. So we're watching it in all its glory, and it's actually showcasing itself to us right here. Now here's the thing that we're doing. We actually have records of doing these images of different objects. And we have a database that Robin Curtis has put together. And that database gives us the opportunity to reference every time we've captured a specific object. So when we do that, it means that now you have the chance to do some actual astronomical discovery, because you can go compare what some of these objects look like over a period of years, because we're capturing, right now we're working on 2 years of data. So if you look at, say, a faint nebula that we had in the view at one point, and then you come back a year later and see it again, or 4 months later and see it again, and you see a difference between the first and second, you could have made an astronomical discovery. That's very important. So we're actually trying to do that. We're actually trying to set this up to be data that can be utilized for research purposes. And any one of you can become a citizen astronomer and do that.
There are a couple of very red stars in that field. One to the lower left, one closer to the lower right.
Right here?
Yep.
Okay, and this one?
Yep.
Yeah, that's also one as well, but it's sort of saturated, so you can't tell. That's also a red star, but you can't tell. These stars could very well be foreground stars, all up here, and those other stars are back here. Or the vice versa, it could be the other way around. We could be seeing these stars through the nebula. Okay, and it might be closer. Don't know. Now, if you notice, we see this right here, but you notice there's another arc out here that's now becoming visible?
Yeah.
And I'll move this down so you can see it. I'll move it over, actually. Might be easier. All right, now what I'll do is I'll get rid of the name, because we know what it is. This is the Medusa Nebula, so I'll pull that out. Okay. Pull that out. There we go. And now I'll try to enhance. So this is, let me show you. Let me pull this back here now a little bit. And then I'll show you. I'll enhance this and you'll get to see what I'm talking about. Okay. Alright, just a sec here. So if we enhance this, you can see that there's other stuff here. Okay, this is an over enhancement. I can actually pull this out and you can see it better from back here. But see this extra loops? Now it looks symmetric, doesn't it? Which is kind of weird. It's heavy over here and not so heavy over here. So how did that form? Interesting. It has to do, in many cases, with the actual structure of the interstellar medium around it. Okay, if the interstellar medium is less dense over here, then material won't snowplow into it like it might on this side. And because there's knots of stuff that are denser and less dense, depending on where you go in the interstellar medium. RJPX, how are you? He says, what's the greenish object left of the nebula and slightly above the dwarf star? Well, the dwarf star is this greenish blue object right here. Is that what you're talking about? Because left of the nebula is over here. And this is hydrogen emission, and the dull green, that's doubly ionized oxygen emission. This is singly ionized hydrogen emission, the red stuff. So let me know what you mean on that, RJP. Be happy to help you.
Michael Hedrick, your answer is yes.
Well, you got to ask his question so everybody knows what he asked.
Mark, I have a question. Is hydrogen red most often what we see in a nebula? Daryl and Mark. Yes, it's hydrogen alpha, Michael.
Yep. Yeah, just remember that there's people watching that aren't reading the chat, so we have to let them know what the questions are. Okay. Just, and Daryl, of course, is correct. RJB says it was off to the left of the nebula before you move it just now. All right, let me. Oh, you talking about this guy right here?
It looks like a green pinpoint object.
Yeah, that's this guy I think he's talking about, and this red one here. You'll see a blue one too every now and then. Those are pixels that decided not to cooperate on the camera, and it varies. All right, so thank you for pointing that out, because I wanted to make sure people understood that, because you're right. That's, see, here's a red one over here, and if you look carefully, you'll see another. You'll probably see another green one. So that's a red dead pixel on this particular exposure. That's a green dead pixel, because these are RGB, red, green, blue pixels. All right, and so they tend to spread out. Okay, so if we have one dead pixel, they may spread to adjacent pixels. So if we zoom in, let's zoom in on that, because that's a very good point to make. Let's zoom right in. Okay, as you can see, this pixel is definitely not part of the star field, right? You can see the separate pixels here, and this is several pixels of failed green pixelation, failed green pixel sensors. So we have that happen from time to time, and on the next exposure, this location might be just fine. So there is typically a random number of dead pixels on every shot.
Zoom back in on that again.
All right.
On that green one, please.
Yeah, all right.
The extremely purple object over there to the left.
I think that is probably a dead blue pixel.
Oh.
Yeah, one of the dead blue pixels, yeah.
Looks almost violet.
Yeah, it could just be the blend with a nearby star image that it seems to be conflated with.
Okay.
Yeah. But look at this. Look at that nebula. This was a good find, huh?
It was.
Who was the one that first told us about the Medusa Nebula? I didn't.
Maya Leon.
Maya Leon.
Yeah, and she showed up tonight. It made me think of this.
Maya Leon, you're a superstar.
She asked about the Maya cluster. Or, excuse me, the Medusa cluster.
Yes.
And I looked it up, and all that came up was Medusa Nebula. So
yeah.
I put it up.
Yeah. Oh, you're welcome, RJP. I know that you're right. It's not actually there.
And it is correct to call it a dead pixel, then.
Yes.
Okay.
But I see, the thing is, this camera is really quite good. So what happens is, you don't see the same spots in the same place for each time you start a new exposure. So those pixels might be active next time, and you might have a dead one over here. And we just have to be aware of that. I'm going to go to 20 on the Medusa, and then we're going to move on.
This was a chili pepper. That'd be about a 10 quadrillion Scoville units, I think.
Yeah, I think it'd be pretty hot. I want to welcome all of you. There's 51 of you out there watching. Hang out with us. That's great. Make sure you subscribe. Because we try to bring the universe to you again. The universe live in real time is what we're all about, and that's what we bring you. Maya Leone says, thanks, guys. You're more than welcome, Maya. You've been here for years with us, and we appreciate all of you who hang out with us. And to the new arrivals, welcome. Hope you enjoy the objects that we show you. And this object, remember, is the Medusa Nebula. It's a planetary nebula, the remains of a star kind of like the sun. When this star finally started to get old, it stopped fusing hydrogen into helium, and it swelled into a red giant. And then as it swelled into a red giant, the core began to collapse more until some of the helium could start fusing into carbon. And when that happened, the star made another track called the horizontal branch, where it actually moved hotter and started turning a little more blue. And then when it ran out of helium, it started to grow again into a red giant, as hydrogen was burning in a shell outside the core, helium was burning in a little shell outside the core, and then it just got larger and larger and larger as that core collapsed more, because of course there was no outer fusion to push the star, hold the star up. So the core began to collapse, which causes a massive stellar wind, which expands the star. And when that happened, the star started to pulsate. And when that happens, what happens here is the outer layers of the star, like out here, actually separate from the inner core, and you end up getting a very distinct shape in the middle, a round shape where you have less material, because that outer atmosphere of the star is literally pushing off of the core and leaving the core behind. And then what you see in the core is the hot blue remnant left over as that continues to collapse, in this case down to a white dwarf, in a larger star down to a neutron star, and possibly with a supernova or a black hole collapse. So this is how stellar evolution works. But what's in this mess coming off the star? What's in this mess is all the goodies in our periodic table, or all those elements that you're made of. You're made of the stuff made from these types of explosions, these types of remnants. Okay, this was a slow motion expulsion of stuff. A supernova is a fast motion explosion of stuff. And all that stuff spreads out into the universe, and you're made from all that. Everything on the Earth, and the Earth itself, and everything in the solar system was made from that. You are star stuff. And as my favorite astronomer, Carl Sagan, once said, that is simply how it's true. We are made of star stuff.
Here's some details on the central star.
Okay.
It's called a PG1159 star, often also called a pre-degenerate. It's a star with a hydrogen-deficient atmosphere that is in transition between being the central star of a planetary nebula and being a hot white dwarf. So it's heading into white dwarf status.
Okay.
These stars are hot, with surface temperatures between 75,000 K and 200,000 K.
K means Kelvin, guys. It's a temperature scale that starts at 0. Absolute 0 is 0 Kelvin, which is minus 273 Celsius, minus 450 something Fahrenheit.
Surface gravity is typically between 10 to the 4th and 10 to the 6th meters per second squared.
Yeah. Now what that means is 10 to the 4th, right? That's 10,000, and 10 to the 6th is a million, right? And if you think about that, our gravity is just under 10 meters per second squared here on Earth. And that star's surface is 10,000, right? A factor of 1,000 more, And the surface of some of these stars has a gravitational force that's 1 million times what ours is, So that's pretty significant. All right, and so there's really no coming back from that if you were to ever try to land on that. There's nothing we know that could withstand it. Not at this point. We'd have to go interdimensional, in fact, to do it. Izabela is here.
Izabela. Hi, Izabela.
Izabela, look at this. This is the Medusa Nebula. Look at it. It's really pretty. I've kept going here. This is 26, and I'm going to keep on going. Look how beautiful it looks. I'm going to add a little extra detail neon sharp mask here. Let's see if we can pull out more detail. Look at that. This is really sharp. Now we're really sharpening it up. Look at that. Wow. Let's go up to 4, all the way up. See, that's too high. Right? But we can bring it down 1.2, 1.3. That's about good. That's good. Really nice. All right. Okay, we're going to pause this guy now and save it. This will be the Medusa Nebula. We're saving the raw file. And then save it exactly as seen. There we go. All right. Beautiful. So, if you want to know where to go to find these images, Daryl or Izabela will put up the link, but you can also go to skytourlive.org and scroll down to the next section, and it'll say "Take me to cool images," and you'll see these images. These are not the highly processed images. These are just our raw processed images. The images that are better, and literally quality to frame under glass. We do work on it. We create these for you. All right. And those you can get by joining the Patreon. All right, let's do this here. But you get the streams are free to see and watch and do anything with us. Ask questions all you want. And I say this often too, Daryl, and you've heard it before. There really is no one else doing this. There's no one else doing nightly observatory runs like this on clear nights to bring you the universe in real time. There's no one doing this. There's people who they'll take pictures of an object. They'll do meteor showers like Bill New York Sky Watcher, which are fantastic. Shots of the moon like P&K Space Imaging. Okay, but as far as the deep sky goes, and managing all the complexities of doing it, which you can see, this is a pretty complex operation here. And to do it from 2,500 miles away from this telescope it still astonishes me. I almost still pinch myself to say it's not real sometimes. All right, where do you want to go next? Let's see. There's a few things we might want to look at. Well, we got the moon out there too. So, Dark Nebula is not going to show that well. It might. We could try it.
Think the moon will be interfering with the comet?
Well, why don't you dig up the coordinates of the comet, and we'll check out the comet too.
Set.
All right. Meanwhile, what I'm going to do is look up another object that we might want to see. Actually, we might.
The comet is off Orion's left elbow now. It's moved quite a bit.
Yeah, do you have the coordinates?
I do.
All right. Go for it.
04 hours, 38 minutes,
Yep.
8 seconds.
Okay. And
declination.
Yep.
Plus 2 degrees, 31 minutes, 5 seconds.
Okay. Okay. Well, now I've put those coordinates in here. We're going to tell the telescope to go there. So you watch the telescope, you'll see it move. There it goes. And we should see a fuzzball. That's quite far. There it is. Right there. Okay, so what we'll do is once we stop and the telescope settles on its position, then we can move it into the center and do this. So let's
I
move
don't
it.
see your key pin. There it is.
Yeah. Well, the screen times out. You know, it's a timeout, which is okay. All right, so you guys may remember
Totally blank for a while.
it does. It goes blank until you start to move the telescope manually. Then it comes back.
Okay.
All right, there's our comet. It's much smaller than it used to be, which makes sense. But this is Comet C22, C's 2022. Sorry. E3, and then ZTF for Zwicky Transient Facility. And it's a beautiful comet. We've captured it over the weeks that you've seen it from us many times. All right, and here it is. Put that out there for you so you can see it. And now we'll do a time exposure so you can see what it looks like now. We are guiding properly, as you can see right here. All right, so we're guiding, and let's now go and do a exposure. Let's do 35 seconds. All right, there we go.
Once you got the stack running, can we go to Stellarium for a moment?
Yeah, once it's running. So I'm going to the live stack, and we'll clear the previous one, which is the Medusa Nebula. Look at that. Again, that's really pretty. That's such a beautiful nebula. My gosh. Oof. Wow. That's going to be pretty to work on. All right. I will clear it, and that's going to be up on the server in just a few minutes. Izabela says, oh no, our comet is leaving us. Yes, it is. But for now, here it is. Okay, this is the comet live as we speak. Okay, the green, that's from diatomic carbon atoms that are being lifted off the surface and ionized, and it's also from cyanogen, which is a carbon atom and a nitrogen atom connected to each other. Cyanide, by another name. And usually those are like a CN molecule, and then there's two of them together usually. But look at that. That's how it looks right now. And let's go to our histogram, our data connection here. And let's color correct first. All right. And then we can zoom in on our comet. It is moving away from us quite rapidly, and when we look at it without the magnification, it used to be bigger than this. It actually, if at full frame, when we weren't zoomed into it, the comet used to be this big on the screen and fill the whole screen with its tail. Okay, but now that it's moving farther away from us, there's slightly less activity on the surface of the comet because the sun isn't interacting with it as much, and the dust tail is still there, but it's going to be fainter, and it's just going to be fading from view. My Michael Hedrick has a question. Mark, do we know how many? Do we know of any double supernovae which occurred near each other at the same time? Well, actually, there are cases, for instance, where stars have gone supernova and they were binaries, and as binaries they also cause their companions to go supernova as well. And I'd have to look up the studies to find the exact ones, but if they're double stars, what happens is the stars go around each other, and they're not right on top of each other. They're actually separated by some distance, by sometimes 10, 20 times or more the size of the distance from here to Pluto, right? So if the star goes supernova of a pair, all right, it may also be orbiting a normal star. Well, that normal star will evolve eventually, as well. But as this star evolves, and this star here that goes supernova has exploded, as this star, I gotta correct this. If this star here is like a sun-sized star, expands into a red giant and then goes down to a white dwarf, like we saw the last two objects, it might be in a binary orbit with another normal star, which itself could expand into a red giant when it evolves. Okay, and when that happens, depending on how close they are, material from this one that's expanding could spill onto the surface of the white dwarf. It goes through the barycenter, the center of orbit, all right, and it'll deposit on the white dwarf. Well, if the white dwarf isn't 1.44 solar masses, it's all good. But if it's 1.44 or 1.435 solar masses and enough gas deposits onto the surface, what can happen is the star can do one of two things. If the star's mass stays less than 1.44, that gas going onto the surface could spontaneously ignite and cause rapid fusion on the entire surface. All that hydrogen gas can fuse into helium right then and there. And if that happens, the star gets extremely bright. And then it will fade over a course of a few days to several weeks. And that's called a nova, not a supernova. Okay? That's a nova. And then the cycle can repeat. And you can have stars that just cycle through and repeat over and over and over. And that's kind of interesting too, that we could do. So that's one thing that's important to remember, that these stars can actually do a nova situation. All right? But if that star is a white dwarf and it's orbiting a star that evolves, and that red giant is now spewing hydrogen gas onto the surface, if it very quickly goes over 1.44 solar masses, then that white dwarf can actually explode and go into a specific type of supernova called a type 1a, Roman numeral 1, little a, supernova. And those are very special supernovae that we see now and then. And they are a certain brightness. They're all a certain brightness. So, intrinsic brightness. So if we see them, no matter where they're happening, in a distant galaxy or whatever, we can instantly know the distance to that galaxy once we do a brightness calculation of it. Because we will know how bright it's supposed to be. And depending on what we see, we can actually calculate the real distance. So we call those distance candles, these type 1a supernovae. And again, those are a white dwarf orbiting a red giant star, where the red giant leaks onto the white dwarf and causes it to explode. So we've done 11 exposures so far. Let's zoom in now on this comet. Okay.
Mark, Terry Hogg asked...
yeah, I turned it down already.
Okay.
Thank you. Yeah, look at that. So you'll notice the distinct color difference. This is the yellowish color that we see. This is kind of like the yellowish white color that we see in the plane of the solar system. This is dust dust tail from the comet. One thing that we do not see is the gas tail. And I'm wondering if the gas tail is still here or if it's no longer present because the comet is moving farther from the sun.
I bet it's still there. It may be pointing away from us too.
Yeah, it was here last time, but it's as the comet moves away, it's probably going to be moving down this way.
Yeah, and getting fainter.
Yeah. So I'm not seeing it, but that's okay. Let's see if we color correct this. Of course, we have the moon out too, guys. That's the other thing.
Yes, Izabela. Mark, Izabela wants to know, are the binary stars placed on the HR diagram as one single object or each one individually?
Individual.
Yeah.
Yeah. And the reason is because they are distinct stars. And if there's a white dwarf, then they're called WD, white dwarf stars. And you'll see those down below what we call the main sequence. If you look and what is the Hertzsprung-Russell diagram? If you measure temperature of the stars across the bottom and brightness across on the left side in a graph, you'll see that the hottest and bluest stars are the most bright up here, and it trails down to the very faint M stars, the coolest ones down here. So the temperature goes from hot and blue on the left here all the way to it goes through blue, bright blue to less blue to white to yellow to orange to red. All right, that's the stars. And then here they go from brightnesses that are below the brightness of the sun all the way up to a million brightnesses of the sun or more. And within that range, we see a lot of stars that are fusing hydrogen into helium like normal stars. And that makes a little strip down the middle of this diagram, as Ejnar Hertzsprung and Henry Norris Russell noticed. And that became something they called the main sequence. That's the main location for normal hydrogen-fusing stars. All right? And then, down below that, less luminous stars, the white dwarfs, okay, ended up down at the bottom, right, underneath that main sequence, and up above were the giant stars. Stars like Betelgeuse, stars like Antares in the eye of the scorpion, or the heart of the scorpion. And the Antares, for instance, if you put it where the sun is, would go out all the way past Mars' orbit all the way to Jupiter. Betelgeuse, similarly, might even go a little beyond Jupiter's orbit. So that's a huge spherical body, you know. But it's not the biggest. One of the biggest spherical bodies in the universe is actually 4 to 5 times bigger than our entire solar system. And that is a black hole. That's a supermassive black hole. One of them is in the center of a galaxy that we'll see in just another couple months, which is Messier 87 in Virgo. It's a big elliptical galaxy, and the Event Horizon Telescope imaged it some years ago, and we actually saw for the first time in human history what a black hole can look like in a telescope. Really fascinating.
And if you take that Hertzsprung-Russell diagram and you go halfway down and halfway across, so you're right dead in the center of the page, guess what's there?
Give him a guess.
The sun is there, our
right.
sun, our star.
That's right.
It's one solar brightness and one solar mass, right dead in the middle of the diagram.
Yep. And everything is measured in terms of the sun. And because it makes sense to do that. It makes sense to do that. You know?
Mark, excuse me a moment, please.
Sure.
Right back.
All right. Okay, we're going to keep going here. I'm going to actually clear this in... well, first thing I'll do is I will name it. Comet C0, or no, C dash, because the slash isn't welcome on the server. They don't like that name. Okay, C slash, or C dash 2022 E3 ZTF. ZTF stands for Zwicky Transient Facility. It's an automated search telescope on Mount Palomar out in California, named after the famous Swiss astronomer Fritz Zwicky. Now, Fritz Zwicky, of course, was a family man. He had a daughter named Barbarina Zwicky, and I think there might have been somebody else, I can't remember. But Barbarina is a member of SkyTour LiveStream. She comes in and she watches from time to time. If she's watching, she may say hello. And if she does, show her some love, because it's because of her dad that we see sites like this. Okay, very, very cool. Okay, so now that I've done that, we're going to save this as it is and save it exactly as we see it. So if you want a picture of the comet, here you go. Then we'll clear it and do another one, which will be coming in right now. Boom. All right. There we are. You'll notice all the noise. That's what stacking does for us. Right? It looks like it's pretty mottled and noisy, right? Well, at the end of the next 35 seconds, when the other exposure comes in, you're going to see this get a lot better. Just very suddenly. There we go. You'll see it. So let's watch. I'm trying to find something for you also, so hold on, guys. Welcome back, Daryl.
Thank you. I thought maybe you'd passed out or something. I didn't hear you talking.
Oh, I've been talking the whole time. I only went quiet for a second as you came back in, apparently.
Wow.
That's all right.
Izabela, Betelgeuse is not a binary star as far as I know.
I don't think it's a spectroscopic binary or anything.
Barbarina Zwicky is here.
Hey, Barbarina. I mentioned her, and I said she'll probably say hi if she's out there, and I think she probably has. That's wonderful.
Mm-hmm.
And I said to folks, show her some love, because without her dad, we wouldn't have this type of thing. We also wouldn't know much about dark matter, because he was a pioneer in dark matter studies as well. Yep, provocative insights. That's a good way to put it, Barbarina. Okay. Okay, let's there we go. Now we can do a little adjustment here. That's a beautiful comet. Okay. We'll save this as well. And save it exactly as seen. Alright. We'll go back to our night vision mode here for a second. So under night vision mode, you can see the comet is a much smaller fuzzy spot than it was in previous weeks. In previous weeks, it was about this big, you know. And we can actually draw a line on the screen and watch it move in just minutes. Now that's a little harder because it's farther away, so the apparent movement is slower. So it takes longer, but what a beautiful comet it was. Okay, let's pull that out there. Barbarina, thank you so much for offering that. I want to read that. Fritz Zwicky, Caltech's first astrophysics faculty, was the first to propose the existence of dark matter and discovered over 120 supernovae and produced the first great catalog of galaxy clusters. That's right, the Zwicky catalog. I used it myself when I was getting my degree in astronomy. Okay. Thank you for offering that up, Barbarina. All right. So we've seen planetary nebula, places where stars end. We saw comets where life begins in a lot of ways. And now what we'll do is we'll take a visit to places where star birth occurs, where stars are born. We've seen where they die and when they die, and now let's see when they're born, what it looks like when they're born. So this is a beautiful cluster that exemplifies that very location in the sky, that very typical location in the sky where stars are born. And this is known as a stellar nursery, or as other people will call it, an H2 region. H Roman numeral 2, II, is a location in the sky where you see red glow. You see the red glow of this nebula already. And if you haven't seen this one, even if you have, be prepared to be stunned, because this is just an absolutely gorgeous nebula, and it's full of dark lanes of dark dust. Dark dust produced by supernovae and released by supernovae to the interstellar medium, because that dark dust is created in the outer atmospheres of these supergiant red stars, and then released to the interstellar medium this way once they blow up. Let's move a little bit westward here to pull in the western side of this thing. There we go. Okay, now we'll watch our guide here. We'll see when we actually are starting to guide, and we're going to do a 30-second shot. We don't need much more because it's a very bright object. You can't see it with your eyes. You might be able to see it from a dark spot with binoculars. And Barbarina says hello to Marc, Daryl, Michael, Hedrick, Izabela, and all the wonderful stargazers joining in tonight. Thank you for the heartfelt welcome. Of course, Barbarina, you have earned your place here with us. All right, so 30 seconds. Let's go, and let's go back into our stack. And you'll see in our stack, you'll see the comet. That's the last thing here. Comet C. C's 2022 E3 Zwicky transient facility object. Fantastic.
Can we see Stellarium real quick?
Oh, you forgot to do that last time, or I forgot to show you. Yeah.
And oh, you're on to the Rosette now. That's okay. Carry on.
Okay. Well, we'll just tell me what you need after this. We'll look at it. Look at that. And we're going to actually go full screen with this one. Look at that. Is that not pretty? Okay, this is the example now of where stars are born. This is a stellar nursery. This is the hot young cluster that has formed inside of a cloud of hydrogen gas, because stars are made of hydrogen gas. And when stars are formed, they form from collapsing clouds of hydrogen gas. And as those clouds collapse, the centers of those clouds start to heat up. And if you get to a certain temperature, then the hydrogen atoms inside become hydrogen nuclei. The electrons are driven off because the temperature is too hot for them to remain atoms. And now you can fuse these hydrogen atoms into helium atoms. The process is pretty complicated. There's several processes. Okay. And for the regular stars like the sun, it's called the proton-proton chain, but it's not really a chain. Okay, but in larger stars, you have something called the CNO process, carbon, nitrogen, and oxygen. And for other stars a little bit more massive, you have, in addition to those cycles, the CNO process, you have something called the triple alpha process, which an alpha particle is a helium nucleus, by the way. Just so when you hear alpha particle, it means helium nucleus, just so you know. Okay, now, let's just let this develop a little more. Okay, and we have right now, how many have we done? We've got 4 stacks so far, and let's pull the telescope out here and go to full screen for this. Look at that. What a pretty sight, huh? This is the Rosette Nebula, all right? And the Rosette Nebula, again, is a stellar nursery. As I mentioned, I'll put that out there. We saw what happens when stars die and what they look like. We saw those white dwarfs, those blue hot white dwarfs in the middle. And now we see the hot young clusters that form for a forming star, all right? The forming stars, rather. And when you look in the middle here, one of the odd things you notice is this weird cavity-looking thing, right? Well, that's actually real. That's a real cavity. And when stars form, they have lots of very powerful stellar winds pushing out. And those stellar winds can consist of radiation, and radiation has pressure, okay? Like when you say you feel the sunlight on your face, hitting your face, well, for very, very energetic stars, that radiation has a real effect. If it wasn't, then we wouldn't be able to consider using solar pressure to drive a spacecraft, right? But then we also have high-energy protons and electrons streaming off of the sun, and this is what we call the solar wind. And so that stuff, all working together in concert with these young hot stars that are full of this type of radiation and these particles, will cause a cavity to open up. It'll push all that gas out of their way after they form. It's like, okay, we're done with you. Move out of here and let us shine. And so in the middle of many cluster or many nebulae, you'll see a cavity and you'll see stars. And so this cavity is formed by that high-intensity radiation and this high-intensity solar wind blowing out from these hot young stars. We know it's a rosette now. I'm going to take this out just for now. Come here, you. Let's zoom in, shall we? Because there's some features in here that are just stunning. And we have a young moon right now, too, so we're doing okay for having a moon out. Now, one thing to notice, remember I talked about those areas that condense gravitationally? Well, here's some right here. Look at these little tiny dots, right? What those dots are, okay, and I'm talking about right here, okay, and right here. Okay, those little areas right there represent areas, and there's more of them. I mean, there's one right here. It's very, very tiny, all right? And they're all throughout here, all throughout here. What these represent are areas that are places where the dust itself is collapsing gravitationally. Now, gas is collapsing in there and gravitationally condensing, and dust is gravitationally condensing in there as well. What does that mean? It means that at some point, a star might wink into existence inside this dark cloud. And when that happens, you might also have enough of this dark dust circling around, which is basically the fundamental building blocks of planets, to make planets. And you could end up having young hot stars with planets around them, because that's where we came from. That's how we came to be. And the universe is one big cauldron of life, in my view. And so we see the possibility that there's life all over the place in the universe. You know, now not necessarily in a nebula like this, not yet, because these are hot young stars. As they evolve, then there might be a time when stars are on the outside will have their own ability to make planets and so forth, because the temperatures in here will drop to something more reasonable. That happened here. We were born in a solar nebula. maybe a nebula that looked like this at one point, for all we know. We don't know now because over time, the hot radiation from the stars we were born with dissipated all of the gas and dust around us to some extent. So we don't actually have anything to look at, but we're in it, so we don't know. From a long distance away, you might see a nebula still here. We don't know. We do know that there's a dust cloud. The Pleiades is part of this dust cloud, and that dust cloud might extend to our solar system. So we might have a remnant of that dust. Now, if you're thinking about, and Daryl's heard us talk about this, when you're thinking about the sun having formed with more than one star, you don't get a bunch of different stars forming at the same time. You get a bunch of identical stars forming at the same time. Why? Because the dust cloud that they're made from is going to be the same composition chemically. All right. So when we looked in our local, neighborhood here of stars, which by the way is North Hemisphere, Southern Hemisphere, all around the Earth in all directions, we tried to find a sibling to our sun, and we found one so far. All right. There might be more, but we found another star like the sun, and when you look at its spectrum, it looks identical to our sun's. A fingerprint of a sibling. So, we formed with at least two, and probably more. Now, there was a thought, and Daryl's mentioned this before too, that at one point that our sun formed with the Big Dipper stars, because they seem to be so close. And there is truly a moving group of stars in the Big Dipper. That actual, look of the Big Dipper, those stars in the Big Dipper, are kind of moving together through space. And it was thought that maybe we were too.
Yes.
Yeah. But it turns out we're not. We're moving in a different direction. So we're not considered part of the Ursa Major moving group anymore. So that was like, oh man, so where do we belong? Where we belong is with another solar sibling, if we could find one. And we did. One other one. There's more. Guaranteed there's more out there. Because stars don't just form one star, they form in a cluster of multiple stars. But why would we separate? Why would we go our own separate ways? Well, there's a lot of gravitational effects on the objects in the universe, right? And nearby stars and so forth will in fact end up having the gravity moving them around and moving them out of their areas that they were in before. And that's what happened to all of our solar siblings. Hey James Rufford, how are you? Make sure you subscribe and join us. Okay, I'll be right back. I'm just going to grab myself water while this is developed. This is just beautiful, so enjoy this. I'll be right back.
Hello, everybody. I hope you're having a good time tonight. Yeah, go out and look Wednesday night, the evening of the 1st of March. Jupiter and Venus will be at their closest that night. It's good to look maybe an hour after sunset. It'll probably be prettier if you look before it's fully dark outside, too. You might remember Saturn was in conjunction with Venus a month or so ago.
Yeah.
And it moved on, and Saturn is now on the morning side of the sun in the sky. It may be pretty bright that you can see it yet, too bright to see it yet, but Jupiter will be following Saturn down into the sunset, and actually Mercury is going to pop up to meet Jupiter before it goes behind the sun, and Mercury will be joining Saturn, taking Jupiter's place. So Mercury will.
Nice.
It'll never get as high as Venus, but Mercury is going to pop up and Jupiter's going to disappear. Jupiter's going to pop up in the morning sky to the left of Saturn. That's the dance of the planets.
Exactly so.
Bonnie's here. Hi, Bonnie.
Anahata 77 is Bonnie. Hello, Bonnie. Nice to see you. Thank you for coming. Well, we're gonna just back out to show you the entire nebula here. Our spacecraft heading out into deep space. Look at that. Isn't that beautiful? I'm going to adjust the I'm going to dock these here again. I'm going to color correct one more time because we can just get it a little better. There we go. Wow. Now that is a beautiful nebula. You have to admit, right?
Sure.
Yeah. So many things to see. Okay, this is 25. We're going to pause it right here. Save it. Save it exactly as seen. And there we go. All right. And that'll be up on the server in just a few minutes. Let's go back to our night vision mode here. That's what you see in a pretty reasonable telescope. Not that size, but be a much smaller segment of it. Alright, so let's go look at something else now. Oh, we haven't looked at this for a long time here. Not that guy. I'm going to go with the Christmas tree.
Okay, I see that.
And I just have to grab the label. That's all I have to try and do here. This will get us there. Okay, that'll get us there. You'll watch the telescope shift to the apparent upper area there. There we go. This is a location known as the Christmas tree cluster. And this is probably, you thought the rosette was beautiful. This area is just filled with stunning nebulae that are just beyond compare. You'll see once we start working here.
The Christmas tree is upside down, folks. The bright star you see right at center, that's the bottom of the Christmas tree.
Right there.
And it comes to a point down.
Yeah, let me just bring us west a little bit and then go south a little bit to bring the top of the tree a little higher up towards center. And maybe I gotta go up a little bit higher to get the Hubble's Variable Nebula, because we want to always include that nebula because it changes. That's why it's called Hubble's Variable Nebula. And it's down here. Here it is. Very fancy nebula. Alright, so then we'll move this over. It's amazing what's hiding in plain sight, guys. Thank you, Izabela. Izabela says the server just came up for her. Hello there, Robert Fracchia. How are you? Good to see you. Thank you for joining. Okay, we're guiding, and this will be... We'll do a 35-second exposure. That's all we need for this. And off we go. All right. So for 35 seconds now, we're going to expose. Oh, I didn't get it yet. Here we go. All right. We'll go into our live stack here. And that was our last one, the rosette. Well, that's the buffer. We'll clear it. And when the next object comes in, this Christmas tree cluster, it will overlay and be read out. And there we go. Now, this is interesting. Right down the bottom here, you see Hubble's Variable Nebula, which is right here. Then you see here in the center an object called the Cone Nebula. And up top here, you see the Christmas tree reflection nebula as part of the Christmas tree cluster. Now, when Daryl said that the Christmas tree that you're seeing is upside down, here's the base of the Christmas tree right here. And then the Christmas tree goes up to here, right? And then up to here. Kind of like that. All right? Sort of the Christmas tree. Now, we sacrificed something. We're trying to get Hubble's Variable Nebula in here. And by doing that, it ends up being that we kind of remove a little bit more of the stuff that's up here. And that's okay. And that's fine. Okay, so we've got 3 stacked here. All right.
Barbarina's wiki mentions that operations at Palomar Observatory have been shut down due to the snow.
Oh, have they? I can understand.
It snowed in LA and San Diego too, I believe.
Well, I'll be in LA next week. I've got to go do a thing for History Channel out there. They have me on a panel to discuss the TV show that I've been doing for a couple of years, several years now, called The Proof is Out There on the History Channel. It's on history, and Michael Primo and I, who are the video and image analysts for the show, will be out there on a panel, and then I'm actually going to do a talk as well, which is kind of cool. The talk that I'm doing is called The Unorthodox History of the Earth, and I actually go out into the audience for this one, and I actually put the entire history of the Earth on a roll of toilet paper, and I go out and I unroll it with them holding different pieces, different segments, and written on each piece are all the milestones. It's about 120 feet long, all these 300 plus sheets of toilet paper. And what's neat is you over that 120 feet from the time the Earth formed to the time where we are in that room at the end of the sheets, you find most of the major activity took place in the last 24 inches, right? And dinosaurs died 12 inches ago on that scale. So they're recent history, not ancient history. And when people see that, it kind of bugs them out a bit. They don't realize just how recent that history is. You know, so neat. You know, all the things that have happened here, you know, the Younger Dryas event, other things, these things are all recent history. Okay, this is the Christmas tree cluster. You'll notice it's some really interesting details in this cluster, right? And this nebula, which is going to come in more clearly, there's a nebula right here called the Phosphor Nebula. You can start to see some of the filamentary structure, right? And then down below, you see this dark nebula cone, right? And that is called the Cone Nebula for that reason, right? So that's very interesting how that all comes together. This is a gigantic molecular cloud of all dark dust in here, illuminated by the stars that are in it three-dimensionally. So you're seeing a big three-dimensional system here. Hi, Cindy Murphy. I didn't say hi to you. Hey, Dr. Fox is here. Dr. Fox 2000 is with us. If you haven't seen Dr. Fox's channel, I was just there the other day, Dr. Fox. You were doing Siggy in Ireland, or Iceland rather. Siggy volcano, you were replaying that. If you guys want to see anything about volcanoes, which of course are a huge life-giving force on this planet, go check out Dr. Fox 2000's channel. Make sure you subscribe to him, because he actually does some really nice work and shares with you and talks about the earthquakes, and he'll show you where the latest earthquake zones are, some of the harmonic tremors that you might get just before an eruption. He knows it all. He goes through it all. And, you know, as someone who is in science, I have to say that it's really fun listening to him go on these beautiful tears and talks about all these things. It's great, because he keeps you right up there, and he speaks at your level. He's not going to go over your head with anything, okay? He knows how to talk to everybody. And that's really kind of a cool quality to have. So welcome, Dr. Fox. Good to see you. And Daniel H. is with us. Hi, Daniel. Yeah, you can see now the Phosphor Nebula is coming in even clearer. Now you're going to see more filamentary structure in here. See that there? All looks good. Let's see what it wants to do. It wants to give us a little more contrast, which is good. That's nice. Let's see how much is actually there. We're gonna just give this a little punch. All right, let's zoom out so you can kind of see. It kind of artificially, not artificially. It shows you an exaggeration of a little bit more what's there, but it's not. It's not an exaggeration per se. This is what's there. You know, we can actually leave that there. As we bring this down, look at that gorgeous, gorgeous location. And of course, this again is the Christmas tree cluster, a stellar nursery. Daniel H. says it's a stormy night in Oklahoma. Michael Hedrick, thanks for subscribing to Dr. Fox 2000. As I said, great volcano site. Great volcano channel. That's fantastic, and I'm glad that you did that. Thank you so much. All right. This is looking nice. We're going to pull this back down to reduce the amount of extra noise we're adding, and I'll pull this one up. Very nice. Let's go back up here.
Oh, darn. Excuse me again.
Yeah. See, there's the Phosphor Nebula. You can see it right there. It's sort of over the reflection nebula that's in the background. So that's dark dust sitting over the top of this blue reflection nebula below. Good night, Cyclone. Thanks for coming. RJP says, Merry Christmas with that frame. Better light display than anything I've seen on the ground. Yeah, it really is. And the thing is, it's a light display spread out across multiple light years. That's neat. Everything you see here is real, and everything you see here is being generated in real time. You know, SkyTour LiveStream, we bring you the universe live in real time. To see more about us, you go to skytourlive.org right here, down below. And you go to the upper left in skytourlive.org, and you go to this stream. Go to the upper right, you can see our Patreon. If you can join our Patreon for as little as $5 a month, you can help us continue to bring this stuff to you. Because we definitely need to do that, because our Starlink costs have gone up. Do you know Starlink has added this weird thing? They actually say that if you have low capacity site, we're at a low capacity site because we're in the middle of the desert. Now it might go to a high capacity site at some point. But if we're a low capacity site, they're going to actually increase our cost. And for high capacity sites, they reduce your cost. So that's kind of weird. So we're going to end up going up in price. And I see Marianne Robb is here. Marianne is one of the movers and shakers of SkyTour LiveStream. She's one of our main founders. I want to welcome her. Show her some love, guys. Because without her, this wouldn't exist. No. Well, the East Coast one would exist, but the West Coast one certainly wouldn't. The Desert Observatory would not. Thank you for stopping by, Marianne. I'm so glad you did. Yeah. Boy, this is really pretty. Okay, we've got 19 exposures here. We're going to go to 20. There's our 20. And we'll save it now. I'm going to pause it first. And then I want to put in a Christmas tree cluster up here. Let's do this here. We'll go. Oh, maybe it did. Huh. Did you see Marianne is here?
Yes, Marianne is here.
Yeah. Okay. All right.
Bubbles variable nebula there at the bottom.
Not yet. I'll move it up and show you.
Okay. That'll be one to look at, and you get more focal length.
Yeah.
There's some really cool things going on inside that little nebula.
Oh, let me show people that. So you just pull out of it. Here it is. This nebula is an interesting little guy because it's there primarily because there's a dark nebula in here. This is all dark nebula, right? And much of the illumination for it is coming from inside a dark nebula in here or in this side, and it's illuminating. It's thought that there's dust going around this star, and that dust going around the star is being it's casting like a shadow. So Hubble's Variable Nebula on some points will be extremely bright, like tonight, and other nights it'll be extremely dim. All right, kind of like this, maybe even more. All right, and we have captured it on various nights at various points across the months where it's been as dim as it can get and as bright as it can get. Really cool looking. Dr. Fox 2000 is asking a question. With this new discovery of the innermost inner core, it seems to be unique to Earth. Hypothetically, could it have been caused by the early planetary collision of Earth and the second Mars-sized body? That's an interesting question. Now, the thing that's interesting about our core is we have a solid inner core, right? An iron nickel core. Why is it solid? It's solid because it's under immense pressure, okay? So even though it's hot and you would expect it to be molten, it's under such pressure that it's solid. Okay. Now the outer core, the core around it, is a liquefied core, a liquid core. Now the inner core and the outer core move against each other, and have traditionally moved against each other in a normal way. But then what's happened is the core, actually the inner core, stopped rotating and started going the other way. And this is actually a cycle that has occurred before, and we captured it previously. And you know, I forget when the last shift was. It was like 60 years or something like that. But man, we went through it. Nothing changed. Nothing's happened to the Earth. It's a normal process. It keeps going back and forth like that. It'll slow down, stop, go the other way, stop, and then go back. That seems to be a normal cycle that it's been going through. So clearly nothing dramatic happens. And I'm amazed the doomsayers don't say the Earth is coming, you know, because they usually do, but not this time. And is it unique to the Earth? Good question. We don't actually have an accurate understanding, say, of the Martian core at this point. The Mars Insight lander that's supposed to give us some ideas because of the fact that the Insight lander is supposed to be able to measure the heat within Mars that's coming out, but that probe that the Martian Insight lander was supposed to bang down in could only go in a few inches. It was supposed to go down like a meter, and it just couldn't get down there. Maybe there's rocks in the way, whatever, depending on where it landed. These are the types of experiments we have to do there, because you literally go, oh, this one's not going through. Try another spot, Frank. Okay. Oh, this one's going down. And the whole process would be done in like 10 minutes, as opposed to months and months and months of retrying, right? But that heat being generated by the planet, that heat transfer to the surface, would give an idea about the core of Mars in more detail, and that's something we still are waiting on. So I'm not sure when you ask about whether it's the innermost core and the outer core conditions are unique to Earth. I would say they probably are in some way, but not probably unique to a habitable zone planet. I think it's unique to a habitable zone planet like the Earth. So we might see this elsewhere. Just a thought. Okay. I think I already saved this, but I'm going to try.
You'd wonder,
Yeah,
I would wonder anyway, after 4.5 billion years of Earth existence, you know, if the moon was formed from a Mars-sized body colliding with Earth, could that be it? Maybe. After 4.5 billion years, I kind of think everything would have settled down into one central mass, but maybe not. And that we look out just to the other planets in our own solar system. The evidence, you know, of large impacts on the other planets.
Uranus.
Like Uranus, you know, it's got knocked clean over on its side.
Yep.
It's basically, you know, tilted. Its pole is tilted toward the sun, in other words.
It's 89 degree tilt. And what about Mars having most of its atmosphere blasted away in a cataclysmic event?
Yeah. And Mars's actual tilt is almost the same as Earth's.
And the thing is, it's literally smaller than the Earth by a substantial margin, but it used to have an atmosphere that held lots of water, and most of that water now is locked up in permafrost on Mars, in the polar regions, and low-lying areas on Mars can have haze and clouds, which is interesting, and we do get dry ice clouds and water ice clouds. But the water ice clouds, when they go up into the atmosphere, excuse me, the ultraviolet rays of the sun can disassociate the H2O molecule. The hydrogen gets lost to space, and the oxygen, has nowhere else to go. It goes down into the crust where it bonds with iron compounds and forms Fe2O3, which is rust. And that's why Mars has that reddish color, because it's rusty, which is really, really something. Hey, how you doing, Laura Newbert? Laura Newbert's here with us. Yeah, we need to talk to you as well, Laura. Sometime soon, actually. So we'd like to set up a time to do that. Okay.
What are we looking at now?
Well, this is the Christmas tree cluster still, but I'm going to move to something else. So, we looked at 2 planetary nebulae, which were the ends of star lives. We looked at 2 stellar nurseries, the Rosette and then the Christmas tree cluster. So, I think it might be fun now. That's not going to work. Might be fun to look at. There's a couple things. Oh, I know what I have to do. I have to reshoot this guy. This is the Seagull Nebula. And we have to go shoot this one again. I'm also thinking, maybe before we do that, we should do the Dolphin Head. Maybe we should do the Dolphin Head Nebula.
Is it close by?
Yeah, it should be. Let me just go confirm it, actually. And the reason is because the Dolphin Head Nebula is another type of object, which is really interesting. Yeah,
What
see?
you said the other day was a wolf ray star?
Yeah. So this is a different type. So we've shown some beautiful stellar remnants, stellar nurseries, and now an entirely different type of object, which is really fascinating. All right, and it's right by this star, so we're going to move that star up here. Move a little south here.
If you're doing wolf rayettes, you should do Thor's helmet too.
I'm getting there, maybe. All right, so we're going to go here. Okay, I think. So we're looking for a nebula that's right in here. This is in it. So let's move a little north here. Okay. So from this position, we're just going to go a little further south. Not much. Right about here and a little bit to the east. If I don't miss my guess, this puts us right where the object should be. Let's go here. And I'll take an image to confirm it. That's the Dolphin Head Nebula. That's what we're looking for. There's that star I was telling you about. Okay, and that is this star right here. So we're very close. And we're going to do a longer exposure and hopefully get this out. Alright, so we're waiting for our tracking to begin. And while we're waiting, we're going to set up a 50-second exposure to start stacking. Okay, we're underway. Alright, and here we go. Alright, off we go. Here's our live stack coming up. That's the Christmas tree cluster region. Now, we're at a whole new location. And this new location shows us a area where it initially looks like a planetary nebula or stellar remnant. But it's not. It's actually a very evolved star. And the evolved star is actually in the process of blowing off its outer layers in a very strange way. And the star itself in the middle is actually destined to be a supernova at some point. And so we're actually looking at, and we'll see it right now, okay, once we correct. All right, you can see this ring right here. You can see this beautiful nebula. Let me color correct. Okay.
I have to guess the Wolf Rayet star is the one in the center of that dim circle, not the bright orange one below it.
This is the guy.
Yeah.
That's it. You can see the circle right here.
So might this be one of those Wolf Rayets that we've talked and heard about? Some planetary nebulas, instead of having a run-of-the-mill white dwarf in the center, some of them were evidently Wolf Rayet stars. Is that what's going on here?
It's possible. You know, it's a possibility. Now, what Daryl's referring to, we've talked about before. But one thing to look at is the sheer amount of oxygen we have here. This is a doubly ionized oxygen that we're seeing here. And normally in a planetary nebula, we'll see doubly ionized oxygen and we'll see hydrogen. Now, in this particular nebula, we don't see that. So this one is more Wolf Rayetish, if there's such a word, than it is planetary nebulish. All right, in terms of its genesis. So, but the thing about a planetary nebula is the central star is a white dwarf, and it's gonna just eventually just get cooler and cooler and cooler over trillions of years. This star, on the other hand, it blew off its outer layers of oxygen and hydrogen, and it's actually heading toward a supernova. So eventually this star will go supernova. So it's nowhere near done yet. It's going to go in supernova, and then that supernova remnant is going to blast outward and maybe even overtake the shell of hydrogen and in time and surpass it, making a very, very complicated object over a period of time. But this is something else. This is really pretty. Let's zoom in and see if we can capture some more detail. Look at that. Beautiful, beautiful loop of green right there. Now, it looks like a loop of green. It's actually a sphere. Okay? And if you look at my fingers here, okay, when you see on the edges, you can't see through my fingers. But when you're at the front, you can see through my fingers. You can see my head even through there. Okay? So you're seeing through less material from the front and the back than you are from the sides. So that explains why many of these objects will appear like spherical objects with holes in the middle. Okay? Holes in the middle versus solid edges. Because you can't see through my fingers, but you can here. So you're seeing in between stuff here, but not here, because you're seeing it along the edge. So it looks thicker along the edge. Right? Alright, and so that's why you'll see these things looking like these expanded spheres like this and like donuts. You know? James Dugan, how are you? Good day down in Australia. How are you? Simon Thompson is also listening, and he's down in Australia as well. Dave Schmidt is here as well. I don't think I said hi, David. I'm sorry. And that's down in Thailand. He's in Thailand. We are an international community with SkyTour LiveStream. So I hope you guys can take some time to visit skytourlive.org and think about maybe joining the Patreon, helping us out. We definitely need it. Yeah, it's good to be streaming, James. Thank you. He says good to see you streaming. Okay. I'm looking here to see if we've got a need to refocus or if it's wind. Okay. Alright, we have to, even though I have temperature compensation on, we need to refocus. I was wondering why we're getting a little bit of soft detail, and that's why. So, we will do this all over again. I don't mind. Not a big deal. Alright, so we're going to do this. Waiting for it to come back. There we go. Alright, and now we'll come down here, take off our temperature compensation, and set up for our focus run again. It's a little bit soft. There we go. So now we'll scan inward again and do our focus run. So we'll wait for that to happen. You'll watch over there. You'll watch the parabola get built, and you'll see the point of best focus appear. Mm-hmm. Okay, we're waiting for our focuser here. So I'm just waiting it out. You'll see that parabola now. The other end is coming up, and you'll see the line going in the middle right about now, and there it is. So that's our point of best focus. It refines. It goes up through. It does 12 steps of refinements, and it'll sometimes end early when it finds the best point for sure. And it did. Okay, so now we can just say go to best focus. You'll watch this get out of focus and then in focus. All right, here it goes. Yep. All right. And now we are sharply focused. Okay, that said, let's go back to our 35 seconds. Actually, I'm going to go to 45 seconds. And we're going to just take off and go to the races here. And it'll be much better than what we see right here. This is not really focused. The next ones are going to be extremely well focused. So we'll clear this.
Mark, when you're done here,
Yep.
Cosmic Ray had asked about maybe looking at Dryer's Nebula.
Oh yeah, Dryer's Nebula. We actually have seen that. Yeah, that's really pretty. It's right next to Christmas Tree, I think.
Oh, yeah, it is in Monticello. Reflection Nebula.
Yeah, yeah, with some dark nebula as well. It's really pretty.
Uh-huh.
Yeah, let's see if we can do that. Alright, so this is going to be the Dolphin Head, which is a Wolf-Rayet star along with its nebula. And let's just do this. Okay. Now, if you're wondering what that donut is, that's an artifact of our system the system is very fast, so very bright stars will tend to cause halos around them, and programmatically we remove those later. Hey, Stranger Sound, how you doing? Very cool. And he talks about it, somebody streaming the sunset down in Florida. Excellent. I'm glad you're doing good. So now you can see some detail already in this. See, when we're now nicely focused, you can see in here some really nice filamentary detail, which is coming out really good. I'm going to just try to coax a little more out here. Yeah, look at that. Now you can see the complete ring. And now let's go a little more dark in the background. Here we go. Okay. Yeah, there's a complete ring of the dolphin head nebula. That's really nice. Sorry about the typo. It's dolphin head, not dolphin's head. My mistake. Let's color correct this.
I don't see a dolphin.
This is the dolphin's beak, as they call it. Okay. All right, let's see here. Back out a little. So we've seen stellar death, we see stellar birth, and now we're seeing future stellar death in explosive fashion. Those others were extremely, the planetary nebula were the slow death of the stars, same kind our sun will go through. This is going to be cataclysmic explosion, supernova quality, supernova country here.
I wonder how big the ring shape is.
In light years?
Yeah. What I'm thinking is if or when the Wolf Ranch blows up, the likelihood we might see a light echo.
Oh, yeah. Maybe.
Off the ring.
Cosmic Ray asks a good question. He says lots of oxygen 3, the blue color, bluish green. He says, where did all the hydrogen go? Well, there certainly had to be some, but Wolf-Rayet stars have this peculiar structure and habit of blowing off their outer layers, which the hydrogen layer, I don't know where it went, and some of them have trouble, showcasing a lot of their hydrogen. But there's various types of Wolf-Rayet stars that are known for doing this particular type of O3 oxygen, doubly ionized oxygen glow. Simon Thompson says, I can't post links, but if you look at Astrobin for processed images of the dolphin head, the image is very apparent it's a dolphin, yeah. And Stranger Sound says, just the sheer amount of stars in the field is mind-boggling. It is indeed, and that's one of the problems with trying to actually see what's going on. So what we do when we do final processing is we actually reduce the star brightness out there And we actually separate the star layers. So you have the star layers up here and you have the nebula back here. And we can reverse them and actually turn off the star layers so you only see the nebula. And then you see all the details of the nebula without any confusion at all.
For what you were saying a moment ago,
Mm-hmm.
The various kinds of Wolf-Rayet stars,
Yeah.
and the apparent lack of hydrogen. I mean, at least some Wolf-Rayet stars, haven't they burned off? Haven't they worked their way through the hydrogen fusion stage, and they're now fusing heavier elements?
Yes, but that's in the cores, remember? Because the sun has a hydrogen envelope. That hydrogen will never get down to the core. So fusion only occurs in the core of the star. It doesn't occur out in the envelope. The only exception to that is the M stars, the very, very dim red stars that we'll see in fields, like some of the dimmest red stars. Those have what's called a convective envelope. The hydrogen cycles all the way down to the core. This is why they live so long. They go trillions of years, because all their hydrogen can end up getting fused into helium, and then they'll expand into a red giant when it's gone. They're not more massive enough to go and start fusing helium into carbon, so they'll end up becoming low mass white dwarfs, carbon oxygen white dwarfs. Let's try to add some more. You can see the detail when we shift through like this to go different layers almost. Alright, that shows you the extent of the entire nebula. Now we'll do this, we'll be able to process this and remove a lot of this brightness so you'll see just this beautiful halo of green.
Okay, the Astrovan image is inverted compared to this one, and like there's a nub up toward about 1:30 or 2 o'clock.
Yeah, right there.
1:30, yeah, that's the dolphin's nose.
Yeah, that's what I was saying before. That's like the beak of the dolphin.
Now I see it.
Hey there, Greg McKay. How are you? The big bad scope, as you saw in the title. This is a telescope right here. You're looking down the barrel. That's the camera right there. It's on the end of the telescope. It's facing out. It's on the front end. This is an f8 10-inch telescope that's been converted to run at f2. It's the only one on planet Earth right now. It's a prototype. And as you can see, it delivers good results. So this is a 10-inch Schmidt-Cassegrain telescope that we added a lens system on called a hyperstar to get us to f2, which is photographically 25 times faster than the way the scope arrived to us when we first got it. Hey, Greg McKay, make sure you subscribe, huh? Hit the like button and so forth. Help us trend. We definitely could use all of that help. Wow, that's nice. It's starting to show some nice details. Thanks, Greg. Thank you for subscribing. That's very cool. We welcome you here. Welcome to the stream. Thanks, C&D boy. It says great show. Well, I mean, that's the idea, right? It's sort of like an alternative television show in a sense, right? And if you guys know anything about me, you know I'm an astronomer. That's what I got my degree in. And so what we talk about is stuff that relates to astronomy naturally. But because of my work with the networks and all the stuff that I do on TV, I want to try and have a flair for the creative and the interesting, and bring you things you haven't seen before, in a different way. And that's how SkyTour LiveStream came to be. I wanted a telescope with an observatory. I dreamed of having an observatory dome as a kid. Who wouldn't? And this observatory dome ended up on my front lawn. I had one for several years. And I ran it by being in it for much of the time. And then the dome became too small. I outgrew it with everything we're trying to do. So I sold the dome, and COVID hit, and I couldn't build the next building. So I ended up being without a telescope for a couple of months. And then we ended up getting a GoFundMe going, which got us that scope up there and that building. And that building is 2,500 miles away from where I am in Connecticut, in the dark, dark sky. If you know anything about astronomy, it's a Bortle 2/3 sky, which is an extremely, extremely, dark sky relative to what most people see. Horizon, Milky Way every day of the year. The telescope had to have a bunch of hurdles overcome. How do we control it from Connecticut? How do we manage it when something goes bad? What are our backup systems if something goes down? And, to some extent, we're still working some of those details out. But we've been going, I know now, out in Arizona. How long has this been going? Like 3 years already out in Arizona? Or is it 2 years? I think Marianne will know, because Marianne is one of the other two people that's in this, along with Tara Diulis.
I think at least a couple now.
Yeah, at least a couple years. Izabela says the dome is on the logo of STLS. That's right. If I just show you that real quick, there's the actual dome with the telescope system. It's actually sitting behind me, right now. And that telescope system has been refurbished. It's sitting back there behind me in my office here. Actually, the underground bunker that I'm in. And so it really actually makes up for quite a bit of excitement when we actually have this observatory back up and running. And we are currently getting another telescope, a third telescope, and it's going to go in another location in Arizona, it looks like. And this one will be a higher focal length telescope. So in other words, we'll be able to see not this wide angle view, but we'll be able to just close in on segments and small areas. So that'll be more for the moon and the planets, and for close-ups of the nebulae like we looked at before, the Medusa Nebula, and the other one that we looked at. Really, really cool. Greg McKay says, I'd love to have my rig remote, but I can't afford it at the moment. All right, let me share something with you, Greg. Getting it to go remote, you can do it for free. You don't have to do it for any cost. If you have a telescope called a GOTO, G-O-T-O, for those that don't know, a GOTO telescope where you can tell it to go to objects, then you can control it for free and get it all done for free. All right? I can show you how to do that. I'm very happy to tell you how to do that. But be prepared to do some work. All right? Because besides integrating this software, all right, this software here that you see, besides integrating that and this and these things, and then my special software down here that you see here, this is actually my telescope control program I wrote. And instead of integrating that, if you want to try and integrate and make your telescope run remote, you have to be able to do some of this other work. It's not hard, but you can do it for free if you want to. Right? And there's ways to do it for free. I did not choose to go down the free route because the free route is not good if you're actually truly remote. if you're that many thousands of miles away from your telescope, you do not want to have anything that can go bad. Oh, you mean have it hosted on a dark sky site? I got you, Greg. Okay. Well, there are places to do that too. The only problem is, it's amounts to more than $1,000 a month to have a telescope there, and that's certainly, I can't even do that. I won't do that. He says he uses something called Nina. Is that what you use? Oh yeah. Yep. Nina's very good.
Greg is doing what you did with
Yeah.
once you got remote at your place in Connecticut.
Yep.
You just, instead of freezing out in the dome, you just sit in the office and
Yep.
tell it where to go.
Yeah, I was using DSLRs as well. I wasn't using a dedicated astronomy camera. But now we're using a dedicated camera so we can get band passes and the special filters I use. The telescope, the astronomical camera can take in a whole range of frequencies that the regular DSLR camera could not. And the DSLR sensor on the camera suffered from its own issues. You know? Yeah. Greg says he'll does the remote when he goes to a dark sky site. He does the remote from his car so he can stay warm. I don't blame you. And isn't it cool to do that? I mean, it's so cool to be able to control your telescope from a distance. It really is. And from your car, you could probably do it with Wi-Fi. The camera we're using is a ZWO ASI 294 MC Pro, a dedicated astronomy camera. It's a perfect camera for everything that we're doing. You know, I'm gonna do 24 shots, so this will be the last one. Here we go, and 24. Okay, so now we'll pause here. Now we're gonna come up here and rename what we're doing. This will be the Dolphin Head, DOL. Should be enough. Alright. And we'll save it. Alright, and save it exactly as seen. Okay. And off we go. And now we go into our 1 second shot here. And that's it. Let's pull that out. We know what it is. There we go. Oh, I forgot what I did. It's not the 1 second. It does that sometimes. It jumps to like 4 milliseconds. And that's certainly not anything exciting. But now we see more stars. Okay. Should we go do Dreyer's Nebula for Ray?
Sure.
Okay. Let's do that. It's a pretty nebula. It's right near the Christmas tree cluster. And it's actually, west of the meridian now, I think.
Yeah.
Let's see. Dreyer's Nebula. I think that's the guy. Here it is. Dreyer's Nebula is pretty cool. Really pretty. Okay, let's do that. With the moon out, Dreyer's Nebula might be a little bit less exciting because the blue nebula might get a little washed out by the bluish light of the moon. But we can try it. Michael Hedrick's asking you about a question. If you answer it, make sure you just read his question. Okay.
Michael asks, should the new space station crew be worried about the solar flare? Evidently there was a X-class flare, 2.2. I just looked on Space Weather, Michael, and I don't see it listed there yet. I know the sun's been crackling with solar flares. There was an M class a day or two ago. I suppose not. You know, I've thought about this, but I've never really learned for sure. Does ISS have a safe space?
It does. I believe the Unity module is shielded, and so everybody would go in there in the case of a X-Class. X-Class, they could go, you know, from 0 to 50 or more, you know, in terms of their intensity. And they're of the solar flares, I think they're the only ones that can go up to that kind of height in terms of intensities. And I think it's the Unity module that's shielded. But yes, they do have to worry about it. So that's a very good point, Michael.
Oh, you mean the new crew that's about to go up?
Well, everybody has to worry about it.
Well, he may be saying, you know, there's another crew going up very soon on one of the Dragon capsules.
Yeah, it's on the pad now, I think.
Yeah. Tonight, tomorrow. I guess
something
maybe
like that.
He's concerned whether, you know, that they picked a bad time to launch.
Oh, they won't launch if they're going to be hit by a flare. The thing is, if the flare, the part of the flare that's dangerous is not the light you see instantly, it's the particles that come in a couple days later. So that's part of the issue.
Yeah.
All right, let's just do this guy here. Let's say 35 seconds here. We're guiding, that's good. And then we'll pop out of this, go into our live stack. This is Dryer's Nebula. I think I framed it well. No, I don't want to do anything with that. I'm going to clear this. Okay. 10 seconds. You see the countdown timer right down here if you can read that. And make sure you're at 1080 on your streams, your stream settings. Here we go. Ready. And I know it doesn't look like much, but look where our curves are. Our curves actually have to be intercepting the data better, like this. Oh, look at that. Wow. So now if we go to our full scale here, go to auto mode here. That's really pretty.
So I assume that's Dryers down in the lower right.
Well, yeah, these are all
Reflection Nebula.
yeah, and then we got this. I wanted to capture this. This is the edge of the fox fur, which goes down to the Christmas tree, which is down here. Makes a great mosaic when we do that. We won't do that tonight, though. Absolutely beautiful. I do want to thank those of you that had just joined us tonight. Thank you very much. Come along. Make sure you come again. We're going to have a good time. It's galaxy season coming up. We're going to be looking at galaxies. It's going to be amazing. And in the next couple months, we're actually going to be adding a third telescope to the mix. Maybe a little longer than that. We'll see. So we're going to actually have a really powerful trio of telescopes. And we're going to build our enclosure out here. I'm opting for a what I'm calling a ground unit, where I'm going to have instead of a building like this, which is a massive 11 by 11 building that the whole roof comes off, we're going to do something a little different to give us a better horizon. This telescope out there we're going to put on lifting columns so that the telescope can rise up in the air and look closer to the horizon, so we won't have the limitation of the walls anymore. Okay, obviously that's not good on a windy night, so we have to pick and choose when we do that. The other thing is out here, we're going to use, because we have winter out here, we don't get it out there, we're going to use a small enclosure. So it can be a little enclosure. The telescope, the building will be only just big enough for the telescope to fit in. You can walk around it in just a second. And then they'll have one of these will come off, and the other one's going to come off and open up like a flower petal and be able to expose the telescope. And then the telescope will have unobstructed views all the way to the horizon, even though in astronomy, the horizon always stinks. It's always got turbulent air and so forth. But this way, it'll be better because we can better manage snow and so forth as needed. Look at this dark nebula. Look at this beautiful hydrogen cloud here. Hydrogen cloud. This is part of the whole Christmas tree cloud area. This is part of the molecular cloud complex that it's part of. Look at these interesting areas over here. I mean, let me point some out for you. This is a reflection nebula here with a tiny little emission component or a Herbig-Haro object. I'm not sure. I have to check. This, of course, is another beautiful reflection nebula. We have a beautiful dark nebula here that's part of the whole Foxford element that keeps going down to the lower left. We have this guy here, which is really pretty. It's an emission / reflection nebula. This is an emission nebula complex right here, very small one. And this is just a stunning area. And all this stuff up here, the stuff that looks black is not for lack of stars. It's actually for the stars being light being absorbed and rendered extinct by the dark nebula that's in front of them. All right, so that's what's going on here. And when the dark nebula, which is actually dust, very fine dust, when that stuff gets hit by the star's blue light, it tends to scatter it in all directions, just like the atmospheric molecules scatter the blue light from our star, giving us a blue sky. The dust in these clouds scatters the blue starlight as well, and so basically that's the nebula's blue sky for the same reason. It's called Rayleigh scattering. It's a process that's well understood. So it's pretty cool. Greg, thank you for coming. We'll talk to you soon. Great to see you. Let's try now zooming in. We'll zoom in on the section that's more characteristically Dreyer's Nebula. Look at that. That's pretty cool. Do a little color correction here. It's amazing. You'll notice that inside this is dark nebula in here, but you'll notice that there's many more of these red stars. That's because you're seeing them through this dark dust. And just like when you see the sunset is red. Why is it red? Because you're seeing it through more sky, and more sky means more atmospheric molecules to scatter more blue light. And that means that more of the blue light from the sun's spectrum is being removed before it gets to your eye, and that leaves the red light and the orange light and the yellow light. And so that's what you see, and that's why the sunsets look red. In the same way, that's why when you look in these nebulae, you see a lot of these red stars. Well, they might not be red. They might not be red. They might be white like some of the other stars, but when they're embedded in the nebula, they appear red because the dust is scattering more of their blue light. The deeper in they are, the more light gets scattered. Yeah, Cosmic Ray mentions the Monoceros molecular cloud complex. That's true.
I don't get the difference. SpaceX says the launch is in 12 minutes and 34 seconds. The NASA stream says 1 hour 16 minutes and 18 seconds.
Well, they might have a delayed broadcast. I don't know. I should have asked Michael today. I was talking to Michael. He works at SpaceX, and I was asking him a question about a particular artifact I saw in a Falcon 9 launch. I should have asked him that question. I didn't think to. Look at that. Really pretty. Let's bring ourselves back out. Look at that. Remember when we look at the Christmas tree cluster, notice how we remember this cluster here that we see right there? In the upper right. That's what it is.
I'm sorry, say that again.
Here's that cluster we see in the upper right at the Christmas tree.
Oh.
Very pretty. Look at that. That's stunning. Okay. Well, we'll stop here at 15. And we're going to call this is Dryer's Nebula. We're going to save it. And then we'll save exactly the scene. Yeah, go ahead.
Nothing. I'm still trying to figure out what I'm seeing at SpaceX versus what I'm seeing at NASA.
Okay. I'm wondering if maybe something is it's a delayed broadcast or something, maybe. I don't know. All right. All right, let's see here.
Probably help if I clip live.
What?
It would probably help if I click the live button at NASA.
Yeah, I got you.
They're saying an hour, 10 minutes, and 29 seconds. And SpaceX, okay, that's, they're saying 10:45, but that's that's Pacific time.
Okay.
And the sky's not even dark in the image, but it's not a live image. They're going live in 9 minutes and 10 seconds.
Okay.
Okay, so never mind.
All right. Okay, this has been saved already. So I can get out. This is Dryer's Nebula, everybody. Then we'll just move on to the next object that we'll look at here. Which I think is going to be the last one.
The last what?
Object for tonight.
Oh. Helmet?
No, I don't want to do Thor's helmet today. I want to try something different. I want to do a preview into the Galaxy season here. Look up NGC 3344, the Sliced Onion Galaxy. We can just try it real quick. You can watch the telescope swing around. Oh, there it is. Let's check it out.
7.1 by 6.5 arc minutes.
Okay.
Relatively isolated barred spiral galaxy.
Yeah, I want to see if we can catch its shape.
Constellation Leo Minor.
Mm-hmm. Alright, we'll do a 25-second shot of it just to make sure we can get it, which I think we can.
The face on spiral is pretty.
Yeah, so we're gonna find out how pretty.
Maybe small.
It's alright. Let's see how it looks. Okay, so there's our previous image. Beautiful. We'll be back to that at some point, and we'll clear it now. Dr. Fox says, sliced onion. Well, let's see, Dr. Fox. Can you handle that sliced onion? Wow, that's actually pretty. Let's zoom in on that. Now, see, folks, one of the things I would do right away is I would check the sliced onion galaxy to make sure that this star, that star, and that star, and all these stars you see in it are actually there. Because if they're not, then it means that we might have found a supernova in one of these galaxies. So that's why we always do that. This one looks kind of interesting, that one there. That's really pretty. Let's see what it wants to do. Wow.
There does appear to be a couple of very bright foreground stars.
Right here. Yeah, you can see if we draw arrows, okay, I'm talking about right there, that orange one. I know that this guy is probably in there now, and this guy is probably in there. Sorry. Right there. That's my guess anyway. You know what I mean? So that might be, that's my guess.
Can we zoom in on that any?
Yeah, I was way ahead of you, see that? Well, somewhat ahead of you. Interesting.
Quite a dark lane there.
Right there.
One to the lower left, too.
And that one there, yeah, you're right. So I'm going to guess that this star is probably in there, and that these two stars are, and that star is. Because if they're orange, it means that they're lower temperature, and supernovae, when they're seen first, are going to be very bright and bluish, or just plain white. So if this was a supernova, it means it would already have been well past its peak and heading into being dimmer and lower temperature. We followed one in another galaxy. I think that was interesting to watch. Over the course of 2 months, we saw it be bright blue, and then it went to orange, and now it's gone.
I don't remember which one that was. It was in Virgo, wasn't it? Or
Yeah.
that time of year.
Yeah. I don't remember the one either.
It was an M object, wasn't it?
Was it M66 or M65?
No.
All right.
I believe it was in Virgo.
Okay.
In that part of the sky, at least.
Okay.
65 and 66 for Leo.
All right. All right, well, we're going to go to 10 here, which is right now. Okay, there's 10. So we'll call this what it is. Okay, we'll call it sliced onion. the galaxy, and we'll save it, and save it exactly as seen, and then come on out. Go to night vision mode again, and now let's jump into our planetarium product here and just check out another possible object. Might have to go up north. We have those. We know those. What's this guy? Oh, Caldwell 7. That's a pretty galaxy as well. If I recall. It's an SAB. I'm looking for one particular one. Let's see now. Boy. Yeah, we're still a little early for Measure 51, aren't we? Or are we?
Maybe a little bit. I mean, that's down.
Is it by the tail or is it by the...
M51?
Yeah, where is that?
It's in Canada's Venetici, below the...
Oh, yeah. Okay, so it's down here.
Below the end of the tail.
Yeah, okay, so we're like here. Yeah. Yeah, that's not going to be high enough for us to get over the building to see at the moment. Alright. Well, that's okay. That's alright. Yeah, not good. Alright. Well, then what we should do is come back to Leo.
Under the belly, under the hindquarters.
Yeah. Let's see about... would we be able to do... We might just squeeze out the Leo triplet. Let's try that. Let's see if we can squeeze out the Leo triplet. Because the hamburger galaxy is cute. I like looking at that. Alright. Let's try it.
I will gladly pay you Tuesday
That's right.
for a hamburger today.
Not now, Wimpy. Good.
Alright, there we go. Oh, I think we might be able to just squeeze that out. Yeah, let me just...
Oh, I would think you can. Leo is pretty high by now.
Yeah. Okay, well there's the Leo triplet, the hamburger galaxy just out of shot. We're going to bring it in. There it is, the Hamburglar. Okay. Alrighty. Go in, go to the west a little bit. Okay. Alright, focus is still good. Okay, so we're going to do a 30-second shot here. Yes, not... No, what are you doing? That's not what I wanted. I hit a hotkey by accident, sorry. Alright. Alright, we're guiding. Off we go. So there's the galaxy we just took. And we're doing a 30-second shot of the Leo Triplet. When this comes up, think about how many civilizations we might be looking at, possibly, out there. You know, get to do that right now. And here we go. Look at that. That's pretty. And we will color correct. And let's bring our background down. That's good. We only have one frame right now, so we're a little noisy. There's two. Immediately got better. Look at that. That's pretty.
Uh-huh.
That's the Leo Triplet.
That's M95, 96, and
the hamburger.
Right?
Yep.
65 and 66 are a little farther over to the east.
Yep.
If I remember correctly.
They are. East or... Yes, east. That's right. No, west. They might be over to the west.
Are these under the belly of the lion or the hindquarters of the lion?
Hindquarters.
Okay.
So you're looking under the belly. That's more toward the west.
So this is 65 and 66.
Yeah, this is, okay, the Leo Triplet, right? This guy. This is measure 66. This is 65.
Yeah.
And then the hamburger galaxy up here is NGC 3628. But yes, we are good with the Leos.
I always get 65 and 66 confused with 95 and 96.
Yeah.
But they're almost neighbors.
Yeah, me too. Let's zoom in on this. Look at that. You'll notice that dark line of dust going through the center of the galaxy like this. It's not going through the center. It's actually a circular galaxy, and this dust is accumulating along that disk, in that disk. It's not going through the actual center. It's actually going around it, and probably part of the spiral arms. So you're seeing it edge on, so you're seeing through all that. So it's a three-dimensional universe you're looking at.
Looks quite disturbed on the right side.
Yeah, it does.
Fanned out a lot, like it might have interacted with one of these two guys.
Yeah, and if you look closely at one of these...
Well, that one looks disturbed too.
This one looks like the one that may have been the most disturbed.
Yeah.
Okay, let's color correct. And do an auto correction here. That's too much. That's alright. So drop this down. Look at that. Look at this. Look at these galaxies. These are really pretty. Okay.
Seen a lot in the one on the left, 66?
Yes, 66, 65, and NGC, whatever it was for the hamburger. Interesting.
Well, we looked at it before, but there's a lot in there.
Interesting artifact in there.
Yep. Blue one right there,
Yeah.
and the part hanging down under.
Yeah. Not sure.
Striations and dark lanes and that.
Yeah, not sure what's going on there. Let's go back up to the hamburger.
It would be interesting if we could see the hamburger face on.
Yeah.
See what the disturbance looks like.
I imagine that's. But one of the things to notice, though, with the hamburger is we have stuff all the way out here.
Yeah. Well, it looks like it's puffed out on both ends.
It is. It looks like it, yeah. And that's probably from gravitational interactions, as you pointed out earlier, with some of these other objects in the view. Yeah, there we go. It's pretty amazing to think that, in this galaxy there's probably, who knows how many millions, potentially billions of life forms of some kind. Same here. Same in every other galaxy we see. And whether intelligent or not, that's a whole nother question. As far as I'm concerned, if we could reach intelligence, another organization or another organism can reach intelligence. It's not just exclusively here. Dr. Fox is asking the distance to the galaxies. This particular galaxy is a distance of around 35 million light years, 35.9. This one here is what's this distance? Probably relatively similar. And the hamburger, let's find out what that one is.
Yeah, about the same for all of them.
Yeah, they're pretty much. This one here is 45 million light years. So what's interesting is this is farther away than this, yet it's so much bigger. So this is a more massive galaxy by far. So between 35 and 45 million light years. Simon, have a good night. Thank you for coming, man. Wow, this is nice. Okay, well, we have Leo Triplet. We're going to save it and then save it exactly as seen. It'll appear up there. All right. Very nice. And we have actually had a real good time tonight, I think. And so I want to thank all of you for coming out and hanging out with us. You hear that music coming in now. That tells you it's the end of the stream. It's our stream ending music and stream beginning music. We start and end with it. So you guys have a good night, and we will talk to you again. Thank you for coming out. You can look up on our server, find it at skytourlive.org, and check out the sections down below. Bring me to the cool pictures, and it'll take you to the server where you can look at all these pictures we're taking tonight. All right. So you guys have a good evening, and thank you so much for attending with us. And I'll bring this to you again on the next clear night. This is Marc Dantonio signing off for SkyTour Livestream. And Daryl, you want to say good night?
Good night, Daryl.
There he goes.
Good night, everybody. Thank you for coming. I hope you had a good time.
I think they did. I think you did a good job. Good job tonight, Daryl. All right, folks. We'll catch you later.